All right, hello, welcome. This is building an end-to-end serverless app with machine learning, data, serverless, all the buzzwords you can fit into a title. They're here. So well, it'll be a kind of a fun journey through a bunch of serverless tools at Google Cloud. My name is Brett McGowan. I'm a developer advocate for serverless on Google Cloud. And what that means is I just would love to hear what you're doing with serverless, what you're trying to do with serverless, what's working well, particularly outside of what's traditionally a service, or the functions as a service, these cloud functions. These are kind of the three guiding principles that I like to think of, and that's sort of what I'll use when talking about what is serverless in Google Cloud. So we've got invisible infrastructure. So you're not worrying about managing clusters or virtual machines or networking, all that stuff. That's kind of handled for you. Scaling up and scaling down is transparent, and most importantly, scaling down to zero, meaning when your code isn't running, or your query isn't executing, or your machine learning model isn't actually training or doing prediction. If it's not doing something, you're not paying anything, except for storage. But generally, as these systems sort of go to sleep and they wake up, your billing is tied very, very closely to that. So these are sort of the guiding principles as we talk through this. And we have a lot of tools for serverless on Google Cloud. We're actually going to touch on all of these categories, from data analytics to compute to machine learning. We don't have a lot of time, so it's just going to be a little bit about a lot of things. I have some other resources. You can dig a little bit deeper into the specific example that we're looking at today to kind of see how all of these pieces really tightly fit together. But as you can see, there's a lot of tools at your disposal when you talk about building a serverless application. And rather than kind of walk you through it product by product and give you the pitch sheet, I thought, let's build something. Let's actually build a complete end-to-end serverless app. And we're going to do it because in my imaginary startup, I have invented a way to do mail order ice cream. And that's going to be the example we have in e-commerce. And actually not just any ice cream. It's going to be specifically soft serve. If you don't know what soft serve is, it's this kind of ice cream. It's not like the hard ice cream that you necessarily get in the freezer. It kind of comes out of a big metal machine, typically. And it's actually not just soft serve. It's actually going to be soft serverless ice cream. And if you're thinking, Brett, did you just come up with this whole idea because you had this goofy pun? Save your questions till the end. It's not relevant. But definitely, yes. So we're going to have this example of a soft serverless ice cream shop. We're going to sell ice cream online. We've got all your classic flavors like blueberry a la Node, pistachio. Sorry, it's going to be one of those sessions, so bear with me. All right. And there's a lot of pieces actually behind making a full, production-ready, scalable application. And this is a lot to take in, so we're gonna break it down. We're gonna do it piece by piece. We're gonna do it in 4 parts. First will be serverless fundamentals. What are functions? What are apps? When do you use App Engine? When do you use Cloud Functions? We'll talk about serverless outside of just compute with some machine learning and some big data. Then we'll talk about serverless outside of Google Cloud platform specifically. And then some things about what does it take to run serverless in production. And again, we're going to just kind of touch a little bit into each of these topics. So I encourage you to follow the link that I'll show in a second. You can dive a little bit deeper. So first, serverless fundamentals, building with functions and apps. This is an e-commerce site. We have a web app. And so in our sort of traditional app model, we've got the presentation layer, which is going to be a web app. It's going to be a Python web app running Flask. And if you don't know what Flask is, it's just like a web framework for Python. It's like Express.js if you use Node. The point being is there's nothing particularly specific about Google Cloud. This is what you would run as your web framework no matter where you're running your Python web app. And what does our presentation layer do? It does things like shows you the cart, shows you the products that you can shop from, right? It renders the HTML to talk to the user. And then from that, we've got some services that are going to be backing this presentation layer. And those are going to come in 2 categories. They're going to be synchronous operations. So things like, what does this cost? Or what is the image for this? And these are synchronous in the sense that when I ask the service for it, I want to get the data back right away. So I need a response now, and I'm going to actively wait to get a response. This is in contrast to asynchronous ops, where the request comes in, and maybe it's a long-running app. Maybe I need operation. Maybe I need to do some complicated data analysis, or I need to do some long-running query, or whatever. So the service will tell the presentation layer, OK, got your request. Thank you. I'm terminating this connection. I'll get back to you later, right? So that's the asynchronous operations. And these are things that aren't as time critical. So if I want to do automatic categorization of my products, or maybe a payment process, like I don't need to, if my payment processor is down, I can't make the end user wait until the payment processor comes back up. Like I'll take it, accept it, we're all good, acknowledge the request, and then handle it later. And then the third layer is going to be the data layer. So this is our database, essentially. This is going to take a list of all the categories that we have, all the products that we have, all the metadata, the pricing, promotions we're running, have people's orders, carts, all that sort of a thing. So now we're going to walk through how to choose which pieces of which when we're building our serverless application. And the first is going to be serverless data. And I like to classify serverless data on Google Cloud Platform into 3 broad categories. So there's data for your application. So this is a database that actually runs your app. So in this case, I'm actually inserting orders into the table. I'm querying to see what products meet some sort of query that I'm querying on, right? My application actually runs on this database actively. Second category is an analysis, so data warehousing. My app doesn't actually run on this database. Data gets fed to this, so I can do reporting on it later. I'm not reading and writing and deleting and modifying all kinds of rows. It's conceptually just like a write only, just dumping data into it. This is sort of the BigQuery. And then data flow, which we won't really get into this talk, is when you need to manipulate your data, like as it comes in batches or it's streaming, you need to clean it, you need to process it, you need to do some complex work on it. Data flow is a good sort of serverless tool for that. But for our app, we're going to focus first on Firestore, which is our serverless database that we're going to use. It's NoSQL, it's a document-based database, and it has some really interesting properties. So scales really, really well in a serverless manner, so you aren't actually going in there and tweaking knobs and setting up replication and backups. That's handled for you. It's a really cool property of real-time updates. And what that means is as your data gets changed in the database, Firestore actually is synchronizing those changes out to all the clients potentially in real time. So if you have 100 people on your website and a change gets made to, say, a price, Firestore can actually push out all of those changes to the clients in real time if that's what you want. And then it's serverless. So again, going back to serverless pricing means if you're not actually querying the data or reading or writing, you're not paying anything except for storage, which is fairly minimal. So it scales directly with how you use it. So that's data. So it's going to take care of our last column, which is the data layer. So now we're going to move into compute. And this is where things start to overlap a little bit, I will admit. So hopefully we have some guidance, I can get some guidance on how to choose what. So the first is serverless functions. This is sort of where my heart lives. I love Cloud Functions. I've been working on it for several years. And this is event-driven, sort of single-purpose functions that run in the cloud. So a file is uploaded and I want some code to run, or a document is changed in Firestore. I automatically want a Cloud Function to run. So just think events that happen in the cloud and your code runs in response to it. And Google Cloud takes care of wiring it up and scaling it. And then down we've got serverless applications, and that's just kind of what it sounds like. So this is outside of just one single purpose function. This is an entire application. So an entire web front end, an entire API. So this is internal routing you're handling state inside of your application. This is, App Engine is a good product for that. And then the newest is Cloud Run. And it's also sort of serverless applications, but it also can be functions because it's wrapped in a container. So it can be any runtime you want, any framework, or any language. Now let's dig in just a little bit. Why would you choose Cloud Functions? So I talked specifically around events. So if you have events you're responding to in the cloud, Cloud Functions is every time that function gets invoked, it will have 1 gig of memory. There's no sort of shared requests across an instance. You can also have it automatically handle retries. So in our payment example, if the payment processor was down and your function bombed, you could have Cloud Functions automatically retry it later. Languages it supports, Node, Python, Go, and then Java is coming. So again, functions, Cloud Functions. Now why App Engine? So in this case, we're talking about a web application, and App Engine is a really good fit for that. It's designed for web applications and HTTP applications like APIs. And part of that is it scales really, really quickly. Much better scaling characteristics, for example, than Cloud Functions, which is good for your user-facing web application. Because if the user has to wait a quarter of a second extra or a second or 2 seconds longer, that can actually turn into lost revenue specifically for you. So you want it to be as responsive as possible. It supports custom domain names. So obviously, if I have a public e-commerce website, I want my own custom domain, which App Engine supports. And just a little bit of a word about scaling. So why is App Engine scale faster or more quickly than Cloud Functions? And that's because App Engine allows for multiple concurrent requests. So that's good and bad, depending on your perspective. It's good because if you have one instance that's handling a request and another request comes in, it'll send it to that same instance. So it doesn't have to spin up another instance and create kind of a brief cold start, a brief delay. And so you could have it handle 5, 10, 50, 80 simultaneous requests before it needs to spin up a new instance. So that's good. That means it can scale to handle a ton of requests really, really quickly without a lot of cold start. But the downside to that is it's shared resources. So if you have one request on that instance that's taking up a ton of memory, it could potentially impact the other requests that are coming in. Cloud Functions, on the other hand, is one concurrent request per instance. That doesn't mean it always spins up a new instance every time a request comes in, because it might have a still hot instance left from a little bit ago, and it'll route a request to that. But you can know that if you asked for, say, 2 gigs or 1 gig or 512 of memory, you have it entirely to you for that one request. No other requests are sharing that instance. So now that we've kind of walked through that, let's go back to our diagram, and then we'll see a demo. So here's our web app. Between Cloud Functions and App Engine, probably not surprisingly, we're going to choose App Engine. It is designed to be a really good web front end. And then let's get into synchronous operations. So again, these are things that we're asking for some data and we want it back immediately. So here we actually have a bit of a decision to make. We could use Cloud Functions. They have HTTP endpoints. You can make a request. It will return a response. But actually for this, we're going to also use App Engine. We're actually just going to have services within App Engine, so it'll scale with our application. It's a bit of a monolithic approach, I know, but it works. And I think actually it makes a lot of sense because you have kind of some shared state across a user object and carts and products. So it can live within one shared code base in your application. So let's see a demo, if we go over to the demo machine. All right, so here is our live website, Soft Serverless Ice Cream Shop. We've got Softy, our raccoon, he's our mascot. We've got all of our classic serverless ice creams, Bananas a Service Split, Warm Start Apple Pie. So we're going to, using App Engine, we're going to add a new dessert. And let's choose, we're going to do an iced cold start. Iced cold start. Your morning coffee served within 2 seconds. Let's see, how much will this be? This will be, it's coffee, so it's expensive, $6. So hit OK, and because those are all synchronous requests, as soon as the page comes back, it's in the database, the image is uploaded, everything is good. And if you just want to see, if you don't believe me, in Firestore, go down here, let me refresh. Here's our Firestore database. Uh-oh, there we go. Oh, it's not sorted. So somewhere in here, clearly it's in there, ice cold start, $6. Cool. So not a lot to it. I just kind of wanted to show you the app, and then we'll build on it as we go. So we can go back to the slides. So now we're going to talk about asynchronous ops. And so for this, we're going to use Cloud Functions plus PubSub. And if you're not familiar with PubSub, it's a message bus. So you can just send messages, arbitrary messages at it, and it scales up to incredibly high throughput, so up to millions of requests per second. And this could be any arbitrary JSON payload, sort of whatever you want to send to PubSub in sort of message. And it has topics you publish to that multiple subscribers can subscribe to. So I could publish one message to say new order or payment completed or whatever, and whatever subscribers you want on the other side can listen to it. And you'll see why this is useful in a second. Because traditionally, if we were to do payment processing in our web app, it might look something like this. We take an order, we process it, we kind of clean up the data, we normalize it, we do some sort of checking, we send it out to get processed as a payment, and then we send the user an email. And that's great, like this has worked for a while. But this has a couple of issues, one of which is, what if there's an error, say, in the confirmation email getting sent, right? And so we need to retry this. Well, now you somehow have to piece together, did I finish processing the order? Did I already send this payment out to get processed? I'm not sure. So instead, what you want to do is break these up into multiple sort of microservices, if you will. And we're going to glue them together with PubSub. Now, PubSub will let you do things asynchronously, or sorry, concurrently. But in this case, we actually have a specific order, right? We need to clean up the data, we need to process the payment, and then we need to send the email. And we're going to use PubSub to connect these, to publish the message, so that, again, if, say, the confirmation email fails, we can just retry that without having to double charge the customer if we retried the whole job. But because we're using PubSub, and you can just connect any arbitrary cloud functions or any HTTP applications to it, with minimal effort, we could do some other things, like maybe we want to capture those order analytics and put it into BigQuery, which we'll see in a second. And none of the rest of the application has to change. We literally just added a new cloud function listening to the same topic that was already getting published to, and it's just going to take that data and put it into BigQuery. So more concretely, here's our App Engine presentation layer. It's going to publish the order data. So here we've got a topic called process payment, or payment process. We have metadata about the order ID, so we could pull it out of the database. We're using Stripe for third-party payments, so we're going to include that token in the message, because we don't want to like persist it to disk. And then that's going to go to a cloud function. There we go. A cloud function that will send it to Stripe for payment and then update it into Firestore. But because we're using disconnected with PubSub, we're going to have that then publish another message to PubSub saying, I have completed the payment, it has been successful, this is what that looks like. Another function picks that up and then sends it to SendGrid to send a confirmation email that, hey, order was successfully processed or not successfully, as was happening to me this morning, and hopefully it doesn't happen in a minute. All right, so speaking of, let's go back to the demo machine. So let's see that in action, what I just saw. We're actually going to do a payment, so let's buy this, what do we want? Peanut butter and Jenkins. That sounds good. And I'll put in my address, so 123 Main Street. This is not my actual address, by the way. I do live in New York, so that is real. And this is my spam account, but please don't email me. All right, so my phone number. And if everyone will look away, I'm going to put in my credit card number. All right, and hit pay. So what has happened now is it's asynchronous, right? So the application immediately took it, returned back to the user, thank you, got it, published a message to PubSub, but the order isn't necessarily actually processed yet because it's all happening asynchronously through Cloud Functions. But if it happened quick enough, I should be able to come in here. Oop, thank you for your order, awesome. And I didn't put any text in there because I'm lazy. But two functions got triggered, right? One to actually process the payment, and then one to send the email. All right, we can pop back to the slides. And then another example, which I won't do as a demo, because I don't think we'll have time, is a reminder. So we've all been to those websites where you add a couple things to your cart, but you don't actually check out, and then they send you an email a few days later like, hey, still interested in whatever? Like, click here, it'll be super easy. So with Cloud Scheduler, which is just Cloud in the cron, you can set up these arbitrary schedules to say once a week or whatever. So in this case, we would say maybe every Monday at 9 a.m., go find any cart that hasn't been touched in a week that we haven't sent an email about already, gather it up, and send the person an email as a reminder. And we'll do it using Firestore to query the database and SendGrid to send the email. SendGrid, I guess I didn't mention, not a Google product, it's just a third-party emailing system, but it's super, super easy just because they have an API. So you just make a REST call and you can send your email. Cloud Scheduler, if you don't know, like I said, it's Cloud cron. So arbitrary schedules. I want Monday and Thursday at 3 a.m. or every 30 minutes or every 1 minute. I want you to do something. You can do tasks within App Engine. You can have it published to PubSub, or you can make it an invoke in HTTP function. So in this case, we would have it call an HTTP Cloud function to send that email. But if you have some third-party system or some system running elsewhere that has an HTTP endpoint, then Cloud Scheduler definitely can hit that on a schedule. All right, so that's our compute. Now let's move beyond into the world of serverless machine learning. So we have an idea. What we want to do is we want users, because obviously we're going to be super popular and we're going to have thousands and thousands of these hilarious ice creams on our store. We want users to actually be able to browse by category. But we don't want to have to manually categorize these necessarily. We want to also automatically categorize them, say, based on the image. So how would we go from an image of an ice cream to some labels? Well, as is required by Google law, I have to involve machine learning in my talk at some point. So we're going to use machine learning. So the first, we're just going to use the Cloud Vision API. You've probably heard of it, but if not, it's just an API. It has been trained with using machine learning, but you don't use machine learning in any way. It's just an API, you call it, you give it an image, and it analyzes it, tells you like what objects are in the image, what is it an image of, colors, things like that. And there are various APIs for text and language and translation, text-to-speech, a whole bunch, video processing, a bunch of these. So that's going to be the first part. This is going to be an easy part. We just give the image to the API. It comes back with these categories: dessert, ice cream, sundae. But there are more specific categories that I want to use that maybe the Cloud Vision API doesn't know about. So maybe specifically, I want to have it labeled like blueberry ice cream or mint ice cream or cookies and cream ice cream. And actually, Vision API does know about some of those, but it doesn't know about all of them. So with a tool called AutoML Vision, I can actually feed it a bunch of images to train it. This is what mint ice cream looks like. This is what cookies and cream ice cream looks like. Minimum of 10 images. We recommend 100 or more, so it really can get a sense of how to categorize these. It will create an HTTP endpoint for you to invoke. And it's serverless because when you submit all the images for training, it spins up enough resources to do all the training based on the images and the labels you've given it. Once it's done, it spins down to 0, so you aren't paying for it. And then when you do predictions, similarly, it scales up to handle the amount of predictions you need. If it's not doing any prediction, it scales down to 0. So how do we actually use this? So we've got a presentation layer. We add a new item. It's going to publish a message to PubSub, say new topic. We'll have two functions. The first function, we'll just call the regular Vision API, get those labels back, and then save them to Firestore as categories. And then the second one will do the same thing, but using AutoML Vision. So these are our custom labels that I have trained this on to recognize blueberry ice cream or cookies and cream ice cream. All right, so let's actually see these in action. If we can head back over to the demo machine. All right, so just to kind of show you what it looks like, so here are some examples of the labels I put in: blueberry, chocolate, cookies and cream, matcha, I don't know how you say that, not hipster enough. Mint, strawberry. But if I click on these, then you can see, here's an example of some of the images that I used to teach it. Here's what strawberry looks like. And so one thing I thought would be interesting, here's mint, and it's kind of like this light green. That's like a very sort of neon green looking color. That's bad data. But then this matcha, it's actually very similar. It's also green, like a slightly different shade of green. So let's see how well this does. So I just loaded all these images into cloud storage, and then gave them the labels and said all of these images are cookies and cream, and all of these are chocolate or strawberry or whatever. So let's have it look at, this one is a mint, and see what it comes back with, because those are pretty close. So you can see it's 81% confident that it's mint and about 18% that it's matcha, because they're pretty similar. So I think that was kind of interesting, and that's not necessarily something that the Cloud Vision API can do out of the box, so I trained it to do that. So let's see that in action. Let's add another dessert and have our custom machine learning label applied to it. I'm going to take, we're going to have one, and we're going to call this Kubernetes and cream. You can really taste the Kubernetes. Pods of chocolate. That's a little Kubernetes joke for you there. And that's going to be $5, and submit. All right, so going back to the synchronous versus asynchronous, you can see right away Kubernetes and cream showed up, but it's actually missing these labels over here, so food, dish, ingredient. But if I refresh, it actually was pretty quick. It was just a second. So the black one is my custom cookies and cream that it labeled, and then the others, the food, ice cream, and frozen dessert, are the ones that the Vision API did. So it actually happens like probably less than a second later, but if you think about it in terms of priority, it's okay for the label to come a second later. As soon as we get that product up for sale, that's the priority. We want that to happen in real time. So that was Cloud Vision API, and then AutoML. So if we can switch back to the slides. All right, so our shopping app can automatically label images and custom labels, but sort of what do we do with this data? How do we make sense of it? It's generating tons and tons of data, because obviously our website is getting massively popular. So we want to take all of that and we want to put it into our big data analytics warehouse, which is BigQuery. And this can handle to terabytes and petabytes of data. You query it using standard SQL. And so it has a compatibility with a ton of tools. So Data Studio, which I'll show in a second, Tableau, a bunch of reporting tools can talk to BigQuery because it uses standard SQL. So you actually can do things that you might not traditionally do, where normally you aggregate your reports, right? So your data scientists can look at it and take, and, kind of plunge and gain insights. You sort of roll things up. But with BigQuery, you can just put all of your data, put all of your web server logs in there, put every event that has ever happened on your website into BigQuery. And it will be able to query and join. You can get really interesting website insights when you go that granular. And I mentioned it plugs into Data Studio. So this is a visualization tool hosted on Google Cloud. Nice and serverless in the sense that I don't have to install anything or run any software. It plugs into Google Sheets, BigQuery, Cloud SQL, a whole bunch of other plugins, has visualizations, and you can actually export it, embed it in presentations, and things like that. So I don't have a very interesting demo, unfortunately, but let's hop over here just so I can show you. So here's our table. I've cleverly named it, make this a little bit bigger, sorry. I've cleverly named it sample data, sample table, and it just has a bunch of events. So especially because we're publishing a lot of things through PubSub, it's really easy to add just a bunch of these little functions that also listen to those PubSub messages. Just take it and then insert whatever relevant data into BigQuery. So you can see, for example, I've been doing a ton of label detection, just label detection. There you go, payment processed. And then I have a very beautiful graph using Data Studio that just connected directly to BigQuery to get insights on what's happening on my website. I don't know if this is going to be big enough. Oh, it is resisting my efforts to zoom. That's nice. But down at the bottom, so overwhelmingly, I was testing some of the machine learning. That's why it's so much label detection. But order created, payment failed, payment processed. Again, it's just capturing all these events, and it's just streaming all the sort of clickstream events that are happening on the website. And BigQuery is able to handle it. It scales up and down automatically. It's a service. You don't have to provision any machines. And it can handle massive, massive data sets. In some cases, like terabytes of data you can query in seconds without having to set up any indices, having to do sharding, anything like that. Very, very cool tool. All right, we'll go back to the slides. All right, so now we're going to do serverless beyond GCP. Specifically, we're going to talk about Google Assistant, which we talked a little bit about this morning in the keynote. So Google Assistant, wildly popular. It's on over 1 billion devices at this point. So this is everything from smartwatches to iPhones to Android phones to computers, TVs, automobiles. There's over 1 million different actions, over 1 million different things that it can do. And it's over 25 different locales, so that's sort of languages and locations. And there are 3 parts to the Google Assistant. There's the physical device. This is the phone or the smart speaker or whatever that has the assistant built in. There's the assistant itself, and that's sort of where you directly talk to Google. So you ask it, and it knows things like, what time is it? What is the weather? Tell me about my calendar, things like that. But then there are these actions on Google, and that's where we come in as developers. We can create sort of custom things for our users to interact with using their voice with our devices. So I'm going to show you a voice interface for talking to our soft serverless ice cream shop. And how it works, so first you have the surface that talks to the Google Assistant. The Google Assistant decides, are they talking to me directly as the assistant, or is this something I can handle? And if so, it responds immediately. But if they're trying to talk to your specific action, or it's something it can't handle, it will reach out to your actions on Google, which consists of a couple of parts. I'm going to use a tool called Dialogflow, which we've talked a little bit about. And this is basically just for doing natural language processing, turning unstructured text into structured text. From that point, once it's figured out what are the things that you're talking about, what are the entities, and what are the intents, what are you trying to find out, then it will hand off via a webhook to your custom logic, which we're going to use Cloud Functions. And this is really nice, again, because it scales down to 0. So if no one's talking to your assistant, you don't pay anything, everything's asleep. As soon as a request comes in, it'll spin up that infrastructure. So we're actually going to talk to the exact same Firestore database to do a query, to be able to talk to our store with our voice. Just one slide about Dialogflow. Like I said, it takes unstructured text and creates structure out of it. So you can see just talking about, I want to play music, there's a lot of things that people can say and in a lot of ways that they can say it. So I could ask by genre. I want to listen to country music. I want to listen to rock music. You could ask for just a specific song, just a specific artist, a specific song by a specific artist. You can just say, play music. Now, if it was up to you to figure out which one of these are songs and which one of these are artists, which ones are countries or proper names, like that's a lot of work that may not be necessarily what you want to spend your time doing. So Dialogflow has a ton of these sort of entities built in to do intelligence around extraction. And also just so you don't have to get the phrasing exactly right before it hands off to your entity or to your custom logic. All right, so let's see a demo of this. All right, so here's my Dialogflow. So there's a few things here. Let me go to intents, and there's a few things I can say recommend. And Dialogflow actually has the ability that it can just respond itself without having to do anything programmatic. So here's some expressions I have, like what is your favorite? What should I get? What's good? What do you recommend? And I just hard-coded a couple of these, right? Like my personal favorite is blueberry a la Node. So if I say, what do you recommend? My personal favorite is blueberry a la Node. Looks like server is unavailable. I feel like it's actually just worked, so I don't think so. But we're probably more interested in doing custom logic, right? So we actually want to have extracted entities and intents. So I'm going to go over here to an intent that says product.list. So I gave it some phrases. Do you have gelato? I want to buy an ice cream. Look for a typewriter. This store used to sell hipster things. But maybe we're expanding our business, ice cream and typewriters. But the point is, it has intelligence to recognize, okay, do you have is not necessarily the important part of this. Gelato is. And I have it doing in a category, but it has a ton of built-in data types. So you can identify, for example, music artist, unit of weight. It has proper names, airports, times, locations. And it actually has intelligence. So if you're looking for a date, and I say, are you open on Christmas? Dialogflow will actually say, what is the next Christmas? Let me turn that into a proper date, so December 25th, 2019, and that's what will actually get passed to your function. So your function doesn't need to know, like, what does Christmas mean? It is going to get a proper date because Dialogflow will take care of doing that for you. And the exciting thing is you can actually integrate this. So now, now that it's actually extracted the entities and the intents into this category variable, we're going to hand it off to our webhook. So we have this webhook, which is running a cloud function. So let's see that in action. And as it does this. So there's a simulator for actions on Google, and you can do different, we call surfaces. So a device that has a screen, a device that doesn't have a screen. And actually, I actually have a live Google Home here. So why don't we actually talk to it directly? Hey, Google, talk to Soft Serverless Ice Cream Shop.
Okay, here's the test version of Soft Serverless Ice Cream Shop.
Welcome to the Soft Serverless Ice Cream Shop.
What's trending?
Everything is trending in the serverless store.
Okay, well, what do you recommend?
I love Kubernetes and cream.
Do you have gelato? Maybe not.
PyCache.io, banan AASPLIT.
So the pronunciation may be a little bit off my ridiculous spelling. Let's see what else do I want to ask. What can I buy here?
I missed that. Say that again.
What can I buy here?
Types of products available include food, ice cream, dessert, dish, ingredient, gelato, frozen dessert, vanilla, sundae.
Thank you.
Deserting me already? That's cold. Just kidding, you make me melt.
She's so snarky. So that was actually live querying our Firestore database. If I had gone in and I had renamed one of these in the database directly, like she would have immediately picked that up. And all she was doing is just querying and combining all the categories that were labeled from the Vision API and sending them back to me so I could filter with my voice. There's actually a whole SDK for doing transactions over the Google Assistant with Actions on Google, with like collecting payment and creating a cart and all that. I didn't build that because there's like a lot more work that I wanted to do for a demo app. But there's a ton of tools available to do that. And I alluded to the assistant supports different surfaces. So in this case, in the simulator, I'm gonna simulate a phone, which has a screen and a browser. So if I say, talk to ice cream shop.
All right, here's the test version of Soft Serverless Ice Cream Shop.
And so similarly, I can say, what do you recommend?
I love Kubernetes and cream.
All right, but if I say something like, do you have food, which before she just set out with her voice.
Machine learning matcha, mint Java chip, iced cold start, Kubernetes and cream, salted caramel cloud, blueberry a la node.
So you can see, not only did she say it out loud, but she actually sent me this little carousel so I could scroll through. Imagine this is my phone. Let me zoom in a little bit. There we go. So it actually, I can zoom in and I can say, oh, mint Java chip, perfect. I can click on it in my phone and it'll actually pull it up on the website on my phone so I can order it. So that way you can kind of take advantage of the different multiple services that are available to your users. You can also do things like, maybe I'm talking to the Google Home with my voice, and it could actually send something to my phone to get more information. So in this case, it could actually send me to the website where I can order this. All right, we can go back to the slides. Cool, all right, so the last section is gonna be serverless in production, and then I'll take a few questions. So let's talk about security. By default, HTTP is open, right? There's no built-in security per se. So say we've got our user who is a bad user, and you can tell he's bad because it's red. And so he's malicious. And it's an e-commerce site, so obviously most of the site is gonna be public, right? We actually want people to go to the site and browse around and see what's interesting and make purchases. But maybe there's an administrative portion, or there's some kind of payment page that we want restricted to certain users. So we need to make sure that this person is authenticated before they go to our App Engine app. So in this example, actually I don't know if I said this out loud. I will put a link, this is on GitHub, so you can see there's more detail about like how to actually connect these pieces, the source code, you can build it yourself. My colleague Chen did a really great blog series that goes even to more detail about how to connect these pieces and how they all tie together. Firebase authentication is great. So it has a bunch of providers out of the box, everything from Google to Twitter, email and password, phone number, so you can have users just sign up with their phone. Anonymous, which is great. So anonymous is particularly great in an e-commerce perspective where I come to the site and I immediately get logged in, quote unquote, which means from the app's perspective, it's a user, they have an ID, they can add things to their cart, but they don't actually have to sign up. And this is a nice user experience because I can browse the site, get interested, add things to my cart, and then as I'm checking out, then you could prompt the user, hey, do you actually want to create an account? And then if they do, you could merge that anonymous account with their authenticated account through, with their email and password or GitHub or whatever. And Firebase authentication makes it really, really easy. And depending on what you choose for authentication, sometimes it's easy just turning it on or off. Maybe you may have to configure sort of what the prompts of the user are as they go through the flow. But, all right, our user is authenticated. We're keeping them out of keeping the bad users out of the sensitive parts of our site. How does this work from a code perspective? What does it look like? Firebase makes it super, super easy. There's SDKs that actually will do all the UI for you if you would like. You don't have to, but you can. There's actually this .sign in with pop-up, and we have this provider here, which in this case is the Google login using their Google credentials. And Firebase actually takes care of the whole flow. Like it pops up a window, asks to authorize, they say okay, comes back, and then you get a callback in your web page that says, oh, the user's authenticated. And there are versions of this for iOS, for Android, and various other platforms. But you also get a token. So if you need to actually make an authenticated API call from the client, you can take this code token, call it to the server, so here's the server code. Firebase also has an SDK for parsing that JOT token, so you can decode it and make sure that this actually is a good user, that they're properly credentialed, that they have the right access. And then here's just an example of you can inject that as middleware in Express so that your app doesn't actually have to do this every time. The middleware will take care of it. So now we're going to talk about a couple of Cloud Functions authentication mechanisms for when you're actually sort of making this production ready. There's authenticating what can call your function, and then there's also authenticating what your function can call, right? So authenticating in and authenticating out from your Cloud Functions. So right now in alpha, there is what we call the invoker role, which is this, who can call this Cloud Function? Who has permissions to actually invoke it? So if you, once this goes live, things will be private by default, even if they're HTTP, unless they have the right credentials. And what does this protect against? So say our user, they're the bad user, they figured out, I can't get to the sensitive part of this web app, but I know there's an HTTP microservice on the other end. I'm just gonna go hit that directly. Because Cloud Functions, by default, if it's an HTTP endpoint, creates a fully qualified domain that you can access from anywhere on the internet. So unless you have it credentialed, anyone can hit that. And if it's a public API, that's maybe no big deal. But if it's some sensitive microservice, like clearly you don't want them to hit that. So you could set up credentials that only the service account that the App Engine app is running under has access to call that Cloud Function. So that way we close off that attack vector. Boom. As dramatically portrayed here. And then next is, what can my function do? And this went into GA yesterday, so it just happened. And this is, each function, you can create its own account and give it very, very specific permissions. And this is good sort of as a, the rule of least privilege for your code to run under. So in this case, we've just talked about, we locked down so that only the App Engine app can talk to that Cloud Function. But maybe we only want that Cloud Function to talk to Firestore. And for various reasons, like just maybe that function gets compromised, it has some node dependency that gets compromised, or some person is doing code that they're not supposed to. We can say that Cloud Function account only has access to Cloud Firestore, so if they try to do, for example, write files to Cloud Storage, they'll get denied because the account that's running under has been locked down. So one of the nice things actually about Cloud Functions and App Engine and Cloud Run is they all run under these service accounts, and by default, they are very broadly privileged, which from a developer's perspective is really nice, because click, 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 you just say connect to Vision API, connect to AutoML, connect to Cloud Storage, and all the credentialing and role, everything is handled for you. But it has the downside of like when you're in production, that service account by default can go to the entirety of your Google Cloud project. So they could be creating virtual machines, they could be spinning up GKE clusters to do Bitcoin mining or what have you. So it's important, like as you sort of go to production, to make sure you lock these things down. All right, that is it. So the URL up there, bit.ly/serverless-store, that is the URL for GitHub that has like the blog post and all the sample code. Some of the code I showed here is not in the GitHub repo yet, but I'll have that in the next couple weeks. But that is it. Unfortunately, it was a sad end to my ice cream store. It turns out sticking an ice cream cone in an envelope and mailing it to someone was not a good business model, but the technology was sound. So, so thank you very much. And I think we have about 6 minutes for questions, if there are any questions. All right, see one coming up here. And there should be a microphone there, yeah.
Hi, great presentation, thanks. So having all these different cloud functions and different artifacts together, what is your recommendation for like versioning? Say your front end is an API with a tight versioning scheme. How would you track that through all your different artifacts?
Yeah, so the questions are kind of around versioning and maybe APIs specifically. So I will say, so for Cloud Functions specifically, there is not versioning. So I guess there's versioning of the API, and then there's also sort of versioning of the code internally. And talking about versioning your API specifically, App Engine is you're going to have to use that. It's the only one that supports explicit versioning. It's nice because it also keeps previous versions of, so it's really easy to roll back. App Engine also lets you do things like deploy without permission, so you can say, deploy this API, but don't actually make it the public URL yet. So it gives you sort of the staging URL. You can go test, make sure everything is good. I will say this, like especially if you're trying to build an API on Cloud Functions and you have a bunch of these disparate pieces, there's not a lot of good tooling yet to actually track and manage all of that. I think that's kind of an active effort in sort of the broader serverless community anyway, just like how do you like get a hold of, it's a little bit easier from an App Engine standpoint when it's kind of this monolithic app that you can control all of it. But once you have, what we call function sprawl, and you've got maybe like 20, 30, 80, 120 functions, it can get difficult to know like, okay, this function, what is that chain, unless it's documented somewhere. So unfortunately, not great answers yet. There are some tools like Serverless Framework where you can kind of document in a YAML file and the workflow a little bit, but it's still kind of early days for those tools as well. So, yeah.
Cool, thanks.
Yep.
Hi, I'm Max Kenner, head of product engineering at Atrium, and my question is about custom machine learning in serverless. So for us, a lot of what we do is working on legal documents, and we have our own custom ML models. Some of those models may take up 1 to 4 gigabytes, and the model itself is larger than the memory limits on Cloud Functions or AWS Lambda, to be blunt. What is the serverless model there? Where it's not just a matter of calling AutoML or calling Cloud Vision, but you actually have to deploy your own model, which is larger than the memory limit or the payload limit.
So you're talking about like real serious machine learning, like with TensorFlow, and like data scientists have put it together. Yeah, so we have there's a couple of things there. One, we have a tool called Cloud ML Engine, which is designed specifically to be used for training and production of like your TensorFlow code, right? And so that is one option. I don't know if you've tried that or not. No. So that is like specifically designed for that exact case. So what AutoML does behind the scenes, Cloud ML Engine will do for you as part of your actual like written TensorFlow machine learning code. If you want a more like traditional sort of serverless approach, Cloud Run, which just came out, could be a good option. It's less serverless in the sense that you have to have a GKE cluster, Cloud Run on GKE could be a good option because you deploy and provision your cluster, and that's just up and running all the time. But it does let you do things like you can attach TPUs or GPUs to it, so your actual machine learning code could serverlessly take advantage of some of the hardware that traditionally you can't do in like a Lambda or a Cloud Functions environment because that hardware is not made available. But you can customize the hardware in GKE. So if you use Cloud Run on GKE, you can customize machine sizes. It can be sort of you could have 64 cores with, 80 gigs of, that's a weird number, but a bunch, how much RAM you need. And so you can really like have much more control with the downside of like you have to manage a GKE cluster. But Cloud ML Engine I would check out, and then maybe just Cloud Run fully managed might also. I haven't actually done anything on that, but the GKE version should help.
Cool, thanks.
Yep. Yes.
What would you recommend for doing CI/CD?
Yes, so the question's around CI/CD serverless. So there is I think a talk later today maybe about that specifically. If you go to this repo, we actually do use Cloud Build. I just build to deploy everything and to run unit tests and things. I just didn't have time to get to it in the talk. But Cloud Build is sort of serverless in that way, like it scales up to do in parallel to do your builds. It's still kind of early around that. People do things like with Circle CI and Travis that are like sort of these hosted. We use Cloud Build for this, yeah, and it's in the repo, yeah. Yeah, do you have a question?
So my question is, like it's very similar to his question about like serious machine learning models. So my question is, okay, now I know that, okay, serverless architecture is there, infrastructure. What about I have like a specific inference server? Can I plug and play that in terms of making that serverless, or no, maybe not? That might not be that easy.
When you mean specific inference server, what do you mean? Like what do you have now?
Right now, let's say I have like all the code for, except the auto scaling, I have everything that you require for a server to do the inference. And can I use this for auto scaling and other than like also the front end side?
Yeah, so kind of going back to the Cloud Run thing, as long as whatever you have can listen on an HTTP port, Cloud Run will be able to run it. You may have to put a Docker container around it to get like whatever your native libraries or your TensorFlow system libraries are. But Cloud Run on GKE or not should be able to do that for you.
Handle that. Okay, cool. Yeah, it can listen on HTTP and also gRPC things.
So gRPC is currently only on the GKE version of Cloud Run, but it should be able to do gRPC. But if you do over HTTP, Cloud Run takes care of like giving you the SSL cert, giving the URL, scaling it up, scaling it down. You just have to give it a Docker container.
Cool. Got it. Thanks.
Yep.
Hi, my name is Ravi and I'm from Salesforce. I have a question with the cloud security that you showed. So you did mention that like a service can actually be blocked from calling another service. How does that work in multi-cloud or hybrid environments? Like when a service from a different cloud or an on-prem service is trying to call into your GCP service? Yeah,
so the question is, how does auth work if the service I'm calling is running elsewhere? So the auth here is all wrapped around, it's based on GCP IAM roles. So probably you would have to do something custom for that. It's something we're working on to have like a more general purpose auth layer in front of, like sort of a cloud endpoints-ish. But for now, it's just GCP IAM roles. So you would have to work around it, I think, unfortunately, yeah, so. Yep.
Hi. Excellent demo, thank you very much. I was wondering if you can share with us a bit info regarding Google Duplex and whether Google Duplex is going to be added to this ecosystem here, you know, being accessible through APIs, or is it going to be behind Dialogflow? Or?
I have no idea. So Duplex, you're talking about the intelligent assistant that like will make calls and do reservations on your behalf. Yeah, I don't know. I think that's sort of outside of the Google Cloud Platform product group, so I unfortunately don't have any insight into that, sorry. Yeah. Thanks. Yep.
Hi, thanks for this. This is wonderful. I had a question about the asynchronous flow that you had. So you had Cloud Functions going to essentially PubSub, and that PubSub would essentially manage the latency that you'd have in whatever the Cloud Function was calling. How would that work for something that's longer latency? So let's say, I mean, the one that you had there was pretty quick. What if this was some kind of a BQ load job or some kind of, you know, something that you would want to be able to monitor and you know, be able to absorb that sort of latency? How would you do that?
So I don't know if this directly is what you're asking for, but there's another thing called Cloud Tasks, which is sort of similar to similar-ish to Cloud Scheduler in the sense that you can queue up jobs, but you can give them like more specific things, like you can control. So PubSub is blast all the things as fast as you can, as many as you can. Cloud Tasks is much more like you can set throttling thresholds, like, oh, I know that I have some back system that like has some capacity that I don't want to exceed, so like don't go above this, don't go above this level. You can have it say like, run these jobs at these specific times. So Cloud Task is a great tool. I did not put it in this demo because it only just got ability to make HTTP calls. It's like in alpha, and it sort of just happened. So that could have also been a good fit instead of PubSub for some of these, for things where you really need to control like throughput and specific timing rather than scheduler, which is like on like a rhythmic time rather than a specific time, or PubSub, which is just like go as much as you can, as fast as you can, as big as you can. So Cloud Tasks might be.
So in that you would essentially do regular polling and then put it back on the task queue if it wasn't done yet.
Yeah.
So
yeah.
from that monitoring. I had one more question, sorry. So I've done a lot of work with Datastore and App Engine, and I know all that is being migrated over to Firestore now. Will Firestore have the ability to do bulk loading? Because that's one of the big detriments of Datastore.
Yes. God, I hope so. I mean, I've run into it as well. I can't speak to roadmap specifically, but the ecosystem's already starting to develop tools around it because it's just kind of a clear need. So personally, I would guess so, but I don't know. I don't have insight into their roadmap specifically. Yeah.
Great, thank you.
Yeah. Mm-hmm. Oh, sorry, we're out of time. I'll answer it down here. Sorry about that. Thanks, everyone.
Hi everyone, I'm Ryan McDowell, a cloud data engineer with Google. Joining me a little bit later today is going to be Albin from Teads, and today we're going to be talking about data warehousing with BigQuery best practices. So if you're coming from your traditional on-premise data warehouse system, or even another cloud, you may be familiar with some of the challenges listed here. When I talk to customers, these are very top of mind. They can't keep up with data growth, they don't have scalability within their current system, they are spending tons of time with teams of people just to manage their data warehouse, they have expensive license renewals, and upgrades for them require downtime. In fact, some customers that I talk to aren't even using data warehouse, or their data warehouse as a data warehouse anymore. They're offloading data from their data warehouse into Hadoop and other places in order to perform the type of analysis that they require in their business needs. And this is really because their data warehouse system is no longer fitting the needs of the business. When we look at why customers, and many customers have decided to move their data warehouse to BigQuery, it's because BigQuery solves many of the issues with your traditional data warehouse system. With BigQuery, you're able to automate data delivery with BigQuery Data Transfer Service. You're able to share queries among users and people within your organization. You can set the foundations for AI and real-time analytics, and significantly reduce the amount of effort required to maintain your data warehouse. But one of the major advantages over the traditional data warehouse systems is BigQuery's architecture. Google BigQuery is fully managed and serverless. Storage and compute are decoupled from each other, and they scale independently and on demand. This offers immense flexibility and cost control for your business, so you're not keeping expensive compute clusters running 24/7. This is also very different than the traditional node-based cloud data warehouse, or even on-premise NPP systems. Some of the secret sauce of BigQuery sits in between the storage and compute layers, in its in-memory shuffle. BigQuery uses remote memory shuffle to gain unprecedented query speed over big data sets. This enables you to query large amounts of data and get your results very fast. Each query that you execute within BigQuery is split up into a sequence of stages. Each stage is then read from one worker to perform some operation from Shuffle and then written back out to Shuffle. If a worker was to, let's say, go down because of a hardware failure or something like that during your query processing, you wouldn't notice it, because what would happen is another worker would spin up and then start reading from the previous point that the previous worker was reading from in Shuffle. This offers you great resilience to downtime and enables you to continually perform your analytics without interruption. And then finally, when a query is complete within BigQuery, after this reads from Shuffle and writes back to Shuffle, and we're sort of done with the entire query processing, the results are written out to persistent storage and then returned back to the user. And this persistent storage enables you to, essentially, if you were to run the same query over again, you get the cache of the previous query. So we're able to serve up consistent results to the users over time. And speaking of storage, one of the major benefits of BigQuery is its managed storage. BigQuery offers durable and persistent storage for your data warehouse, and this helps you dramatically reduce your data operations. Gone are the days that your DBAs are calling you up on the phone and saying, hey, we need you to delete data out of the data warehouse, we're getting too big. That was exactly the scenario at my previous company, where it was a regular basis, the DBA would call us up and tell us to start deleting data. And we didn't want to delete data out of our data warehouse, but we had resource constraints and we had to. And so with BigQuery, you're able to ingest petabytes of data and basically throw at it as much as you can. And when you throw data into BigQuery, all data is compressed and encrypted by default. This means that your data is secure once you migrate to BigQuery and it's in the cloud. And not only is it encrypted, but when you save a record to BigQuery, it's not that that record ends up physically on disk somewhere. Those records are split up into tiny data blocks and smeared across thousands of disks within our data center. And each individual data block is encrypted with a different key encryption key. Which means if I went to the Google data center and just pulled out a disk drive, can't read your data, because it's smeared across everything, and it also is encrypted at the data block level. And you also don't have to worry about data replication in DR, because in BigQuery, when you are running in a regional configuration, your data is in multiple zones within a region. When you're running in a multi-regional configuration, your data is spread across multiple geographically distinct regions. And so you don't have to worry about downtime from just a region or a zone going down, because you'll have that durability and consistency across regions. Now, the first thing that you'll probably end up doing with BigQuery, whether it be in a pre-prod environment or a sandbox environment, is loading data. With BigQuery, batch ingest is free. It doesn't consume query capacity. And so this is huge, coming from a lot of the traditional on-premise systems where you have to carve out separate resources just to deal with batch loading data. That doesn't exist within BigQuery. You can load up data using the communal slots available to you and load it without having any impact on your query capacity. When you're loading data, it has ACID semantics. This means that I can replace an entire table that may be terabytes in volume, and the user would never know that that operation is happening, because the operation is only exposed to the user once it's fully complete, or if it fails, it's never exposed to the user. So you don't have these situations where you have to worry about, oh, I have users querying the data, I can't load it this time. And I don't have situations where I have impartial data loaded, and so people are getting bad results when they're doing their reporting. Finally, you can, like I said earlier, load petabytes of data per day. There's no real limit on the amount of data that you can load into BigQuery. And so a lot of times when I see customers move over to BigQuery, they may be moving over with, let's say, 100 terabytes, but then they end up using substantially more than that on BigQuery because of pent-up demand within their organization, and they're able to just scale as necessary to deal with that. And then finally, there's a streaming API for real-time. So if I needed to ingest real-time records or near real-time, I can stream thousands to hundreds of thousands of records into BigQuery without any impact to my query performance. Which actually brings us to our first best practice. So BigQuery supports a wide variety of file formats for data ingestion. Some are going to be naturally faster than others. When optimizing for load speed, prefer using the Avro file format. Avro is a binary row-based format, which enables us to split it and then read it in parallel with multiple workers. In fact, in a recent test with a customer, we found that Avro would deflate compression to be an order of magnitude faster than the other methods of loading data into BigQuery. Now, Parquet and ORC are also binary-based formats, and they're relatively fast for loading data. When I'm talking to customers, they often think that since Parquet and ORC are their columnar formats, and I'm loading into managed storage, which is also columnar, that it should be, the fastest way to load in. But when we're loading data, we're actually taking the entirety of the record, so we're not taking advantage of any of the columnar format, and there's a lot of random reads. So loading data via Parquet and ORC is fast, but not going to be as fast as loading data from Avro. And then finally, here at the bottom, we have CSV and JSON compressed. Loading data from compressed files, specifically CSV and JSON, is going to be slower than loading data in any other format. And the reason being is because since the compression of gzip is not splittable, we have to take that file, load it onto a slot within BigQuery, and then do the decompression, and then finally parallelize the load afterwards. So it's going to be, there's going to be more overhead, and it will be slower than loading data from these other formats. And after I loaded data into BigQuery, I'm probably thinking about how am I going to do transformations within my system? Should I be doing ELT or ETL? What is the best practice there? So in general, you want to prefer ELT over ETL where possible. BigQuery is very scalable and can handle large transformations on a ton of data. So generally, when customers think about doing ELT versus ETL, ELT is where they're going to start within BigQuery. It's also quite a bit simpler because you could just write some SQL queries, transform some data, and then move data around between tables and not have to worry about managing a separate ETL application. And then as you're loading data in, what you may find is that, well, I have a CSV file maybe, and the date isn't really in a standard format. How do I get this into the data type within BigQuery? Well, you can have separate scripts or ETL processes which process that and pre-process it before loading it into BigQuery. But you can also leverage federated queries onto GCS to transform that data and load it in a single step. Now, the only downside of this is this will consume your query capacity, but enables you to keep everything in SQL if you just have a bunch of one-off use cases for this. Once you've started loading data into BigQuery, in general, within your warehouse, you're going to want to leverage raw and staging tables before publishing to reporting tables. The raw table essentially contains the full daily extract or a full load of the data that you're loading. The staging table then is basically your change data capture table. So you can utilize queries or DML to merge that data into your staging table and have a full history of all the data that's being inserted. And then finally, your reporting tables are going to be the ones that you publish out to your users. And your users are going to execute queries against these tables, and they may be dimensionalized in a star schema, or they may be denormalized depending on the use case. And that method of going from staging to reporting using merge statements, that's where you can perform your SCD type 2 transformations. So if I have the history of records all within my staging table, I can easily, within my merge statement, mark a record as expired and then set the new date for the current record. And then finally, when you're getting into streaming loads or really complex batch loads, you can leverage data flow or data fusion to speed up those pipelines. So oftentimes when I work with customers, they're starting out with the ELT as their primary mechanism of loading and transforming data into BigQuery, but then they may have some really gnarly batch process that doesn't really fit into SQL cleanly. And this is where they'll sort of skill themselves out. They'll start utilizing data flow or data fusion to speed up those loads and transformations and do more complex activities on that data. And if you're getting started with streaming, I recommend using the Google-provided Dataflow templates. So Google provides Dataflow templates for loading data from multiple different places and moving data around. You can find those Dataflow templates within the Dataflow UI. So within the Create Job From Template button, you'll find all these Dataflow templates. And if you find that it mostly fits your use case, but I want to make one slight modification, all those templates are also open sourced. So you can go to the open source repo, you can modify the code to fit your needs, whether it be adding some windowing in, or you just using it as a baseline for your own pipelines, and then quickly accelerate your development. And this is sort of like an end-to-end example of change data capture coming into BigQuery. So with some customers, they may have Oracle, and we'll be capturing the changes in Golden Gate. We'll publish those records to either PubSub or Kafka to ingest those records in real time. If we're doing batch loads, we may just load that data into GCS as our landing zone before loading it into BigQuery. And then we'll utilize Dataflow or BigQuery batch loads to get that data into our raw tables. Then once the data is in our raw tables, we can utilize Cloud Composer to schedule queries within our BigQuery system to move that data from raw to our change log, then dimensionalizing it for our star schema. And this is a very standard process that I see a lot of customers utilizing. Now, once we have a strategy for loading data, it's time for us to think about, well, how do we want to design our schema? In general, I find that customers will overthink this step up front. They'll think about, like, well, let's redesign everything for BigQuery. It's a new system. Maybe I need to denormalize everything. But in general, the best practice is actually to migrate your star schema and Snowflake schema as is, and then optimize as necessary. This enables you to find what may not run as quickly within BigQuery, and then optimize it after identifying those gaps. Denormalization is not a requirement, but it can speed up slow analytical queries by reducing the amount of data that we have to shuffle. So to give you an example, there was one customer that I was working with who had 77 joins in a query. I was impressed that they were actually executing a query with 77 joins. And what we found is that, well, you know, a lot of this did not need to be a join statement. A lot of this was like a country field, or it was a date dimension. It was stuff that could be naturally denormalized into the output table. And so we were able to reduce the 77 joins that they were doing down to 4 joins, which made it a lot more scalable as their data volume grew. And speaking about denormalizing, BigQuery has capabilities for nested and repeated fields. And this enables you to store semi-structured data very naturally within BigQuery, and then query over it. Now, oftentimes, like, this is a very different concept than people used to, you know, row-based architectures where they're not necessarily storing semi-structured data within their data warehouse. So for leveraging nested and repeated fields, I generally have like 3 guidelines. 1, leverage them when you have tightly coupled or immutable relationships. If I have an order and I have an order line items table, the line items will never really be used without the order table. And these are naturally coupled, oftentimes immutable, and I'll denormalize that into a single table. So as opposed to having the order and the order line items table, I can have an orders table that has a list of line items. Similar ways to do that is with sessions with events. So an event within a session, I can have, as opposed to having a separate table for sessions and events, I could have a list of events within a session record in a sessions table. I'll also think about using this for infrequently changing data. So country, region, date dimension, hopefully these are infrequently changing. And so this is stuff that you can actually just merge into your reporting table and have it be slightly more denormalized and easier to query for the users. And then finally, simplifying queries. A lot of times, you know, the queries for users will be super complex, and just by nesting in repeated fields, you can sufficiently decrease the complexity of those tables and the usage. Which brings us to our next best practice, partitioning. Partitions in BigQuery physically split your data on disk based on ingestion time or based on a column within your data. As seen within the diagram, each column of data is split according to the partition key, and then queries over that partition key, as opposed to scanning the entirety of that column and all data within that column, we're able to do partition elimination and only scan the data that's necessary to answer that query's question. And this provides huge cost benefits, but also huge performance benefits, especially on large fact tables. So as a best practice, whenever you have a fact table or a temporal table, utilize a partition column on your date dimension. And as your users are using these tables, oftentimes what I found is users will forget to supply a partition key. So they won't get the benefits of the performance of partition elimination. BigQuery has an option in which you can require a partition filter on the table, which basically means that if I'm a user and I execute a query and I don't specify an as-of-date filter, if I'm partitioned by as-of-date, then my query will return back an error and basically say, I didn't specify a required partition filter. And this enables you to avoid inadvertently scanning large amounts of data, to essentially keep your costs down and avoid errant queries by users who may not know better until they're actually presented with that error. Clustering allows you to physically order data within a partition. So you can do clustering by one or multiple keys. So if I had a partition of 2018-603, I can physically order the data for user ID in that partition. And that way, when the query is executing, we're only scanning a very small subset of that partition. And this can provide massive performance benefits when used properly. You're going to want to prefer using clustering on common filtered columns, especially within your fact tables. So if you had, let's say, a sales fact table or transaction fact table, you may want to partition it based on transaction date, but you may want to cluster it on, let's say, region or store or customer ID. And this will enable you to have better performing queries over that table. Now, you can only have one clustering key per table. So it's basically, most customers will look at the queries that they are running and then determine what is the best clustering key that will satisfy most queries that are running against this table. When you're filtering on clustering columns, you want to filter in the order that they're specified. So when you specify, let's say on that transaction table, that I have partitioned by transaction date and then I'm clustering by, let's say, region and then store, if I was just to provide a store filter to my query, then I'm not taking advantage of clustering. So you want to order your clustering keys properly so that it can essentially limit the amount of data scanned per query. And then finally, most people will ask me, how do I do clustering on a table that's not, has no date dimension? So let's say I have a dimensional table and it's product or it's customer, and I just want to cluster on that customer ID or product ID. Well, you can utilize natural partitioning on that table and cluster based on that column. Even though the partition means nothing, it'll still provide performance benefits. You can also utilize a fake date column within your table and then cluster on customer ID or product ID, and that'll provide even better performance because everything's going to end up on sort of one partition, and then all the data is going to be ordered within there. And then, finally, this is sort of a workaround today. If you had like a use case where you have a dimensional table and you have maybe an integer key, in Alpha, BigQuery has support for integer range partitioning. And so if you're interested in that functionality, you can sign up for that Alpha and begin testing that out. When customers are coming from systems which have sequence generators, there are oftentimes questions of how do I handle surrogate keys in BigQuery? BigQuery doesn't have any sequence generator. And their first attempt at this will often be, well, I'll use row number. I'm doing ELT, I'm going to use row number, and that's going to give me my sequence over my table. But that's not a scalable solution, because when you're using row number in that way, everything within the query is ending up on a single partition, and then you're doing basically a sort of, could be millions or billions of records. A more scalable way to do this is to prefer UUIDs in place of sequence surrogate keys. And then if you have the use case where you need a deterministic surrogate key, you can use a hashing function such as SHA-256, which enables you to hash over one or multiple business keys, and so that you can have a deterministic key be generated every time. Now, once I've loaded data into BigQuery, I've designed a schema, I may be worried about how to manage workloads once users start using the system. But before we talk about workload management within BigQuery, it's important to understand how BigQuery executes queries. BigQuery has a fair scheduler. What this means is that if I was to execute a query in BigQuery, just a single query, it has full access to the resources available to it. So in this case, it's a project that has 2,000 slots, so that query has full access to those 2,000 slots. Now, it may not use those 2,000 slots because the number of slots that each stage requires is based on the number of parallel inputs to that stage, but it still has access to the full 2,000 slots. Now, when I execute two queries within BigQuery, we subdivide those resources. So as opposed to that one query having access to 2,000 slots, now we have two queries that have access to 1,000 slots each. And then so on and so forth as you execute more queries, the resources continually get subdivided. Now, there's a common question there is, well, how do I prioritize between queries? Maybe there's some queries that I care a lot more about that I don't want to have necessarily equal resources available to as much as my other queries. So this is where you can take advantage of BigQuery reservations. BigQuery reservations allow you to create reservations of slots, assign projects to those reservations, so you can allocate more or less resources to certain types of queries. So in this case, I have a dashboarding project, I have a data science project, and I have an ETL project. I may want to allocate more slots to my dashboarding project because those dashboards are being utilized by my C-level execs, and I want to make sure that the response time is always quick. And I don't really care, about my ETL project or my data science project. They can sort of get results as needed. And this allows me to sort of prioritize between the different workloads that I'm executing within BigQuery. And an important thing here is that by carving out resources in this way, you're not carving out data silos, because idle slots are seamlessly distributed between the different nodes within your reservation. So let's say that my dashboarding project is not using 1,000 slots. That means that any other project within my system can take advantage of it. These aren't physical resources that you're sort of segmenting off and putting away, and if you have low utilization, then you're just paying for compute that you're not using. You're able to efficiently distribute these slots across all these reservations, but also have that priority so that if a dashboarding query did come in, it sort of preempts the other projects and is able to take advantage of those full 1,000 slots. And this is also where the separation of storage and compute comes in handy, because we're segmenting off compute resources, but we don't have to think about storage. Storage still exists somewhere in some project, and any project and any user can access that storage, provided that they're permission to that storage via our standard ACLs on datasets. So this brings us to another best practice, is to segment your users based on roles. So as opposed to having everybody in one project accessing BigQuery, the same project which you're storing all your data, segment out your users into different projects based on their role within your organization. So I may have a separate project for my data science team or a department's data science team, and a separate project for my data analysts. And then, if I needed to start doing that prioritization among the different groups, I can do that very naturally just by assigning their projects to different nodes within the reservation hierarchy. So once I have workloads executing, I probably want to know, well, what's going on in my system. BigQuery logs all admin activity and data access into Stackdriver logging. So you're able to access all the logs of what is going on within your system and do analysis over them. But in most cases, customers will want to do analysis over that in BigQuery. And so as a best practice, we actually say, export your data access logs back into BigQuery. That way you can query over those data access logs, and you can have those data access logs in a single place. So you could have thousands of projects using BigQuery, but if you use an aggregated export of those logs to a single BigQuery project, then all that data is going to exist in a single place. All that audit data for your entire organization in a single data set and easily queryable by people who are interested in knowing what's exactly going on. And then finally, as a best practice, is go the extra mile and visualize your data audit logs in Data Studio. By visualizing your audit logs, you can analyze spending trends and query volume over time, and break down costs by project, by user, and be proactive about tracking expensive queries. So I actually have a short demo here. There we are. So this is an audit dashboard that I built on top of the audit logs within my project, right? So using the audit logs, I'm able to get at slot utilization over time. I'm able to estimate the cost of the queries that I'm executing. I'm able to then filter this down by different tables that are being accessed. I can even filter this down by hour of day. So I guess I'm active 24/7 sometimes. And you're able to also filter this down by user ID. So if I wanted to filter this down and just see the logs that are the queries that I am running, I can filter that down. I can see the estimated cost of all the queries that I've executed. And then I can go in here and I can see these are all the queries that I've executed. Maybe potentially there's a query in there that is substantially more expensive than the others. I can then take a look at that and analyze it and see if there's a way to optimize it. And when you have an organization of end users, they may not always write the most efficient queries. So visualizing your audit logs in this way can enable you to be proactive about tracking down those expensive queries, and then informing those users of better ways to run them, and also track those costs per user or per project. Back to the slides. All All right, so that's a little bit about BigQuery best practices. But now Albin from TEADS is going to come up on stage and talk a little bit about how TEADS utilize BigQuery within their organization.
Thank you, Ryan. 3 years ago, I moved from San Francisco to Montpellier, south of France. I joined TEADS in Montpellier and had the privilege to work on a project called BigQuery POC at the time. Today, I am thrilled to be back in San Francisco to showcase how BigQuery has grown from a proof of concept to our main data warehousing system. I'll start with an overview of how we use BigQuery. I'll explain why we chose Flatrate and how we manage our workloads. And we'll finish by the impact that BigQuery has had. But first, a few words about TEADS. Anyone heard about TEADS? Not a lot. Although I'm pretty sure you regularly see ads served by TEADS on these news publishers. So we are an ad tech company. We have united the best publishers in the world into this global media platform. With TEADS, advertisers can reach 1.4 billion people monthly. We serve ads at scale within a premium context. Now, why BigQuery? This is the kind of user interface that we build for our clients. For publishers to monitor their inventory and monetization, and for advertisers to manage their campaigns. It's full of dashboards where you can see plenty of metrics and in which you can explore multiple dimensions. We want a fast and interactive experience, and to do that, we need to collect, store, and process billions of events. Let's take a look at the sources of these events. To do that, we need an ad break. So what happened here? This ad experience emitted 5 events so we can know what's going on. The first one is ad slot available. That's when there's actually room for an ad on the web page. Then we have ad available. This is the result of a complex auction system that is running behind the scenes to select the right ad for the right person at the right price. Impression is when the ad is actually displayed. Then user click and video complete are useful metrics for advertisers. 10 billion events a day. That's more than 100,000 events per second that we have to collect, store, and process within our systems. Another important metric is 10. We are only a team of 10 to give meanings to all these events. That's why we are more than happy to delegate to BigQuery the complexity that comes with that scale. Now let me tell you where we come from, what made us choose BigQuery at TEADS, and how it slowly became our main data warehousing system. So all these events are first stored into Kafka. Before BigQuery, our data pipeline was following the principles of the Lambda architecture. On the batch layer, we were storing the events on S3, and then Spark jobs were aggregating these events into Cassandra tables. The speed layer was doing some of these aggregations in real time using Storm. This model was complex. We had to maintain 2 code bases, and it did not scale well. The cost of Cassandra was getting out of control, and we were limited in the features that we could build upon it. In 2016, we chose BigQuery to overcome these limitations. We also chose to simplify the data pipeline with a single data flow process to load all the events into BigQuery. We also chose an ELT approach as opposed to an ETL approach, meaning we first store all the events into BigQuery and then use BigQuery only to process these events. Let's have a look at this ELT. So data flow is loading all these events into BigQuery using batch mode and writes 1 table per batch every about 30 minutes. The events you see in these tables are unordered. Then the ELT, BigQuery takes over here, and we do several jobs inside BigQuery from these tables. I'll give you two examples. The first one is a simple job that takes all these events and appends them into a single federated table. And this table is very important for our data analysts to run exploration queries or for debugging purposes. The second job I will show here is the rollup job. This job has two purposes. First, it groups events by one table per hour, so we can know where to look at the events. And the second role of this job is to aggregate these events so we can query them much faster. Let's take an example with 5 events that we have. So each of these events have a timestamp, an ad ID, and a website ID, and the name of the event. In this example, we want to group into 3 dimensions: the hour from the timestamp, the ad ID, and the website ID. And we want to compute 3 metrics, which are the number of impressions, of start, and clicks. In this example, we've grouped these 5 events into 2 lines, so that's a 2.5 compression ratio, whereas in real life, our production job can perform a 70x compression ratio. Now, before BigQuery, to do that at scale, we had to run complex Spark jobs written in Scala. With BigQuery, it's been simplified into this simple SQL query. As you can see, we are grouping by our dimensions and computing the metrics in the select statement. In production, we have 60 dimensions and 150 metrics. I can tell you the query is much longer, but it's not more complex. It's just as simple as that. In production, this query runs in 1 minute and 40 seconds, despite having to group by 60 dimensions and process 100 million rows per batch. And the good thing is, it saturated the equivalent of our 3,000 slots for only 8 seconds. It means we have plenty of room to run multiple queries like this at the same time. Speaking of slots, I'll now explain why we chose flat rate and how we manage it. The most common pricing model for BigQuery is the on-demand pricing, where you pay $5 per terabyte of data you scan. Flat rate is an alternative pricing model. For $40,000 a month, you get 2,000 dedicated slots, regardless of the amount of data you scan. If you're scanning few enough bytes per month, it makes sense to use the on-demand pricing. No capacity planning, no commitment. You only pay for what you use. If your bill reaches $40,000 a month, you have 2 options. You can either reduce your usage or optimize your query so to reduce your bill, or you can go flat rate and try to make the most out of it. At TIDS, we chose the second option. It made us focus on building value from BigQuery's unlimited power, rather than optimizing and cost control. It encouraged also other teams to use BigQuery too. In 3 years, TIDS costs has kept stable, and we only had to increase our slot capacity once from 2 to 3,000. And by the way, a few days ago, Google announced that flat rate is available from 500 slots, so the entry price is now about $10,000 a month. One of the challenges of flat rate is workload management. With flat rate pricing, you're not counting the bytes you scan by your query, you're monitoring your slot usage. At some point, you'll reach saturation of your compute capacity. That's okay. That means you're getting the most out of BigQuery. But you have to make sure some of your workloads are not impacted too much the others. You have to make sure they are not starving the others. Throwing money at the problem is always the easiest solution. So it helps, but it's not a silver bullet, as you may end up starving all, not starving, you may end up saturating all your slots, and you still have no guarantee that some of the workloads are not starving the others. Splitting different workloads into different projects helps the BigQuery scheduler give a fair share of slots for each project. This way, a given project cannot impact too much the others. In this example, the orange project is using most of the slots, but when the green and blue project needs some, they can access a fair share of it. Another way to isolate workloads is to implement hierarchical reservation. With reservation system, you can assign slots to nodes that are groups of projects, and you can make the slots sharing unidirectional. In this example, we've isolated the most critical projects into the critical node, and they get 1,000 dedicated slots. They can also access the 2,000 slots of the other project, whereas the other projects cannot have access to the critical one. This makes sure that critical projects always have a minimum of resource available. Now that I've showcased how we use BigQuery, I finished by the 3 major impacts that it had at Teads. It made us build products and features that we were not able to do before. It made data accessible by everyone easily, thanks to SQL, which is a game changer when you compare it to Jupyter Notebooks, and thanks to a UI with single sign-on and built-in security. And last but not least, it made us focus on building products and not maintaining infrastructure. We use AWS Redshift 2, and to give you an idea, we spend more time operating clusters of hundreds of gigabytes on it than we spend time operating BigQuery with hundreds of terabytes. Key takeaways: BigQuery gave us performance and simplicity. It made our data accessible. Flat rate drives usage with predictable costs, but requires workload management. If you want to know more about our data pipeline, our engineering blog has phenomenal articles about it. Honestly, they're great, and I'm not only saying that because I wrote them. Finally, if, like me, you prefer sunny south of France over the 101 commute, we are hiring. Thank you so much for listening. Ryan and I will now be taking questions using the Dory app or directly from the audience.
My mic live?
Yeah.
Oh. All right, question?
Yeah.
How do you manage deletion of user data for maybe GDPR compliance purposes when it's being transformed and stored in like a raw format?
Great question. So there's actually a session tomorrow. I believe it's getting the most out of BigQuery that goes into some of these topics. Essentially, you can utilize encryption functions within BigQuery to encrypt your data via encryption keys and then store all your encryption keys in a single table. And then that data can be copied from place to place, and I don't have to worry about where that data goes. And when I want to get rid of that user data, I just delete the encryption key, because at that point, no one can actually access that data. I encourage you to attend, I think the session is DA 217, but I can confirm that. We'll go to the back mic. We'll go back and forth.
How do you transfer your dimensions to BigQuery from some other database like MySQL or something?
Yeah, another great question. So we have a bunch of partner tools out there. So Fivetran and Illuma are very popular cloud-based tools in which you can ingest data from multiple different data sources. If you're coming from some systems, we actually have a BigQuery data transfer service that you can utilize for migrating both schema and data. Currently, the BigQuery data transfer service supports Redshift and Teradata. So if you're coming from one of those systems, you can utilize that. Otherwise, we have a bunch of partner tooling out there that can help you migrate that data across along with its schema.
Hi. So two-part question. First is, have you benchmarked BigQuery against Apache Arrow with Spark and like doing joins and stuff to see if BigQuery is faster? And is there a plan to add support for Apache Arrow? And second question would be, because I come from a payment processing company, one of the largest in the world, so we have like analysts 500 analysts that use BigQuery all the time, and a lot of the times they're basically doing the same joins over and over again. So we actually had to build a tool that, scans queries and sees regexes and suggests them that, oh, they go to this tool to find out what are the pre-join tables, so that not everyone is doing the same join over and over again. So does BigQuery have any that kind of tool which like suggests that, oh, you're kind of doing this join again, this table is already pre-joined available here? Just thinking out loud.
Yeah, both good questions. So as far as Apache Arrow and BigQuery, I myself haven't done any benchmarks against it, and I'm not sure of the roadmap on Apache Arrow, but it's something that I can definitely look into. And then the second question was
frequent access patterns.
Yes. Frequent access patterns. So today, there's nothing that's going to pop up and say, hey, you're doing this in this way. You should probably think about this other way. But our goal, I would say, watch this space, because our goal within BigQuery is really to simplify complete data operations. So we want to make it very easy for you to provide recommendations and that type of stuff. So I would just say watch this space, and we'll see if something's coming at the end of the year.
Okay, looking forward to it.
Hi, my question is regarding execution plans. Is there an easier way to check the query execution plan prior to executing the query?
So today you cannot check the execution plan prior to running a query. You'll have access to see how much data that query will scan, as well as utilizing tools such as like BQMate. You can see how much this individual query will cost, but there's no execution plan that will be returned back prior to the query executing.
Thank you.
Up front here?
Yeah, so if you're suggesting transformations go into BigQuery and doing the transformation within BigQuery, is there anything for workflow management coming out? Just because a lot of dependencies can occur in the transformation step.
Yeah, so I mean, you can utilize something like Cloud Composer is actually very popular and utilized by multiple companies, in which they're utilizing Cloud Composer to execute those queries. So, and they're also within Cloud Composer is basically your managed service of Airflow. Okay. Within Airflow, you can set pools. So let's say you don't want to execute like 100 transformations all at once, but I want to limit the amount of transformations that are occurring. I could set a pool that's basically a semaphore for like 10 slots, right, and then I'll execute 10 queries at once, and then it'll sort of manage that for me.
Okay, got it.
So this is the question for the TEADS. The dashboards that are running out of the BigQuery, are they exposed outside of TEADS? Some of your customers or vendors are accessing those dashboards?
Yeah, these dashboards are exposed to our clients, but these are like back office dashboards, so we don't have a lot of traffic going into these dashboards.
So the dashboards are directly connecting to BigQuery, or is there an intermediate layer between BigQuery and the dashboards?
No, right now these dashboards are hitting Redshift, so we export data from BigQuery to Redshift. But actually, the BI thing that was announced today could be a nice addition to BigQuery that could have this sub-second latency that we aim for in these user interfaces.
Okay, thank you.
And for the next question, I see that we have some questions on the Dory. Can we switch to the demo machine up here? So this top question, is there any way to set quotas to users and roles to avoid overuse? Yes, you can set quotas on how much data that someone can scan. You can set quotas and limits on those users. And so within the quotas UI, within Google Cloud Platform, you can set those quotas and manage them there. And then we'll, I guess, switch to the top mic here.
All right. You mentioned that, for example, if we have data already in Google Cloud Storage bucket, and we want to load that, let's say the data is in JSON compressed format, and is there a way to make a table that would not ingest that data again, that is like managed by Bigtable, and just use the already compressed data that we have on a bucket, and not being able to pay twice for the storage?
There's nothing inbuilt, but you can manage that within like a workflow management tool, such as like Airflow, to avoid duplicate ingestion and that type of stuff. I see that we're out of time. I'm getting like the red card here, so we'll conclude it with questions here. We'll be around in the hallways and that type of stuff. If you want to come up, feel free to come up and chat. Thanks, everybody.
Thank you very much.
Good afternoon, everyone. How's everyone doing after lunch? Hopefully no one's going to fall asleep. Awesome. I will do my best to keep you engaged, I promise. My name is Mike McDonald, and I'm a product manager on Google Cloud Platform. I've worked on Firebase for about 5.5 years, so I've been building mobile apps for a long time. And today, we're going to go through a couple of the kind of best practices that I've seen that build secure apps. And kind of conversely, I've seen a lot of insecure apps, right? I've seen websites that I can go to and download an entire database just because they didn't follow a couple really simple tips. So first of all, just to level set, how many people have used Firebase, or how many people have heard of Firebase to start with? Great, awesome. How many people have built an app and shipped it on Firebase? Okay, about half the room. Awesome. So if anyone needs to, feel free to run out of the room and just start screaming if you see something that you're doing wrong. And then, we can hopefully fix that really quickly. Otherwise, for the rest of you, hopefully it's not too repetitive, but we're going to go into a lot of really in-depth examples of how to build secure apps on Firebase. So hopefully this isn't too old hat, but if you wanted to build a kind of traditional mobile or web application, you'd build something like this. So your mobile app or your browser talks to a web server, and that web server is, say, running Python and Django, or maybe it's running Ruby and Rails, things like that. And within that server, not only are you doing the business logic of what your application does, but there are a lot of ambient concerns that you have to deal with. You have to authenticate your users. You have to make sure they're authorized to do what they're allowed to do. Maybe you have to validate schema because you're writing to a database or some other API. And then you have to deal with a bunch of other things of just running and managing infrastructure. So, doing OS or language runtime updates, unless you're using some serverless compute, maybe you're not doing that. But the point is, there's a lot of stuff going on that is not directly related to what your application is doing. And so that's the whole premise of Firebase, right? Firebase is eliminate that middle tier server and let your applications talk directly to managed infrastructure. So let them talk directly to a database, or let them upload a file directly to a cloud storage bucket. And that obviously presents a lot of issues, right? Like untrusted clients on the internet. The internet is a very scary place if you haven't already spent a lot of time there, right? There are, if you just look at web server logs of a web server that you run, say on a GCE instance, you see IP addresses coming from all over the world, right? People are doing malicious things on the internet. You want to put yourself kind of ahead of the rest of the internet by doing a couple of really little things to really make yourself secure. So we're going to go through those tips by building an application, right? So we're all at a conference. I did not travel very far. I live in the Bay Area. But I'm sure many of you are here, and you have to expense things, right? So I don't know how tedious of a process it is at your companies, but some companies, you have to fax receipts in. It's terrible. We want to build a better expense reporting experience, right? So I want to take a photo and have that photo somehow magically become a number, right? We can use fancy machine learning things. I've heard a lot about that. And we'll actually use Firebase to build this experience. I think we can do it really, really quickly. So I have myself, and the first thing that I need to do when I'm building an application, and we're talking kind of any normal application, I need to authenticate myself. I need to say, hi, I'm Mike, and I need some way of actually proving that. So I can get information about myself, and then I need to upload that photo. And so we're living in a Firebase world. I can use cloud storage for Firebase and suck that photo right up off my device and drop it in a cloud storage bucket. And then we can use the magic of Cloud Functions. So Cloud Functions are kind of event-driven compute off of various services. So whenever an object is dropped in my storage bucket, I can trigger a function. And then I'm not a super savvy developer. I'm just going to call the Cloud Vision API. I'm not going to write my own OCR or any of that. I'm just going to let Cloud Vision OCR it. And my function will get the response, look for the largest dollar value on a receipt, and then write that information to Cloud Firestore. And then Cloud Firestore, maybe we want to say aggregate over the total sum of my expenses so that I can get that number. So maybe that'll trigger another Cloud function. That Cloud function will do a sum, write back to Cloud Firestore, and then notify me, the user, in real time of, hey, you've uploaded this expense, your sum is now X. And normally, you could build this app where your file storage is public on the internet, and your database is readable or writable by anyone. And those are obviously very bad things. So let's walk through how to not do that. How to kind of do that security as we're building the application. So my tips are structured. We're going to talk about a tip, and then we're going to talk about the mitigation along the way. So as I mentioned, the internet is a very scary place. You should never trust things on the client, because your clients can look something like this, right? If you've built a web app on Firebase, I'm sure you've copied and pasted this config snippet a million times. It literally has an API key, the location of all of your resources, etc. And if you leave your resources public on the internet, someone can do that. And they can just say, oh, I'm going to just write to your database anywhere. So you really can't trust the client to do anything securely. We've provided a number of tools in Firebase that help mitigate these risks. But I get this all the time. People are like, oh my God, this is scary. This is out in the world. Like, yes. And it's by design. And it's not a problem if you follow the rest of the tool or the tips in this presentation. So the first of those is, right, I just said trust nothing. But we have to trust something, right? Otherwise, we can't really do anything. And so the way that we do that is via Firebase authentication. And so we're going to go into a brief, I guess we're going to explain how Firebase authentication works and why we can trust it and kind of use that as the root of trust for the rest of our application. So how many people have signed in via Google? I would assume almost everyone in the room. Great. If anyone has looked at the information that you get back information like a user ID, you get a profile picture URL, you get obviously your Google ID. And you can imagine a world where you want to say talk to Firestore, and you just pass along those claims. You're like, hey, I'm Mike, you know? And Firestore is going to be like, wait, like anyone could say that they're Mike, right? That doesn't make sense. And so identity providers have taken to providing you an access token. So if you've ever done OAuth programming or similar, you get this access token. And that's this kind of opaque string that just represents you. And we can actually take that and Firebase auth, we can kind of pass that along and say, hey, I've signed in via Google with this access token. And Firebase auth can say, hey, Google, like, is this actually a valid access token? Has Mike proven that he is who he claims to be? And Google will be like, yep, you know, I can verify that that access token is correct. And Firebase auth will say, okay, great, Mike has signed in with Firebase auth. Let's actually give him a user ID in Firebase, right? Because we can have people sign in via Google or Facebook or Twitter or a custom provider. We kind of need, you know, some standard that we can all rely on within the Firebase products. And so we'll give you a UID. And that also allows you to do things like, you know, a user signs in anonymously, and then we can upgrade them as they sign in and merge those accounts. We'll give them a user ID, and we will also say, hey, take this other cryptographically signed token. So if folks are familiar with a JSON Web Token, we give you this JSON Web Token that says information about that user. So it looks like this. It's this long kind of seemingly opaque string, but it has three important parts. It has a header, and that basically says, this is the algorithm that was used to sign the token, etc. And then this is the juicy part. It has a body with a bunch of data. And that data has all the same kind of provider-specific information. So things like the name, the email, the name of the application used, and then some other custom claims, like, hey, I signed in via Firebase, here's my Google, or I signed in via Google and Firebase, you know, here are my various emails. And then it has, and this is the most important part, it has a signature. So there's no prior knowledge of cryptography necessary, don't worry. But basically what happens here is Google has a public-private key pair. So one thing is secret, your private key, and then we offer a public key for verification. And Firebase auth will kind of translate that Google credential into a Firebase auth token that it signs with its private key. And so it basically signs the header and the data and puts that in a signature. And so if someone comes along and they change, you know, they intercept your token and they try and change it, that signature no longer matches. And right, when Firestore or Cloud Storage or any of those Google properties will try and understand that token, they'll say, hey, something's wrong, the signature doesn't match. And so that is kind of where our root of trust comes from, right? And it would be obviously very bad if, you know, those private keys leaked. And so we rotate them and we do all of those security things so that you are not trying to build your own identity provider. You know, don't roll your own crypto, don't build your own identity providers. There are lots of people who have done this. So, you know, we have done the mistakes so that you don't have to, and then we fix them along the way. So now when I want to go and query Firestore, I can say, hey, here's my JSON Web Token. Pass that along, and then Firestore knows how to validate that and pull a bunch of claims out of that. So there you go. It can say, awesome, you're Mike, you're this user ID. Here are all the properties associated with you. Which gets us to our next part, right? So we know who our users are, and we can verify and trust that they are who they claim to be. But there are a couple of other steps, right? We've done our authentication of just, yes, you are who you claim to be. But now there's the authorization step of, can you do the thing that you're asking to do? And then, because again, we don't provide you a server to do all these things, we have to say, okay, how do you do schema validation? So when you upload a file, it looks like a certain way. Or how do you do business logic to validate that someone isn't inputting malicious data? And that's where security rules comes in. So Firebase security rules kind of stand between your client and the backend that you're accessing to provide you those additional features. And it does so via this thing called attribute-based access control. So some of you have probably heard of role-based access control, and we'll talk about that a little later. But attribute-based access control is just, here are a bunch of properties. So the user ID, the request that you're making, the resource that you're accessing, go and derive some decision based on that. So we'll walk through that. Hopefully some of you have seen this before, but if you haven't, not a big deal. We typically start by defining a service. We're writing rules on storage, and then we offer this kind of match construct. And so we say, if anyone, for instance, has used the RESTful APIs for Google Cloud Storage, storage.googleapis.com/b/the name of the bucket /o/the path to the object, we're just doing the same thing. We're saying, okay, let's match kind of a RESTful path or the resource that you want to access. That little squiggly character is a wildcard. So in this case, we're going to say, hey, match the bucket in your project. And similarly, we can say, okay, let's imagine that we're naming our the images that we're uploading to cloud storage for Firebase. This users, the name of your user ID, expenses, and then expense.jpg or expense.png. And then I can do these allow constructs. So I can say allow a read or allow a write if some condition is true. And this is the attribute-based part that I was talking about earlier, because those attributes could be if the user matches the user ID that we're here, or a number of other things. So we'll start with the first one, and we'll say only let a user read their expenses or write their expenses. So this request.auth.uid, we're basically pulling a field out of the token and matching it to a name of the file. And then we can make it a little more complicated, right? We can say, okay, any user can read only their documents or only their expenses, but now we are going to enforce a few more constraints on writes, because we don't want someone uploading a 5 GB tarball. We want someone uploading a thing that has to be an image less than a megabyte. And again, we can pull in those attributes and make decisions based on that. And then lastly, we can enforce certain pieces of business logic. So imagine you don't want to allow an expense to be overwritten because maybe someone is trying to change it to look differently after the fact. They've photoshopped it to have a different value. And so we're going to say we're going to require that they can't overwrite their object. So if there's already an object there, we don't let them write it. So that's kind of a very simple example, but hopefully it shows you the power and flexibility of these rules. Okay, so we've uploaded our file. We've done so because we authenticated. We wrote some rules to ensure that it's the correct thing. Now we trigger our function. And so our function could look something like this. If you've ever written Cloud Functions for Firebase, you pull in this Firebase admin library. We'd also pull in a Google Cloud Client library for Vision. Right, we're going to make one call out to the Vision API to OCR. We are going to write a little bit of code that says, hey, find the biggest number on the screen. And then we're going to write that out to Cloud Firestore. And the one thing that I really want to emphasize here is we're actually running as an admin. So this function is kind of not running as an end user. It has a higher level of privilege. And it's actually running using a service account. Right? So we signed in our users with Firebase authentication, but all of our compute is running as this kind of robot service account user, and that uses Google Cloud IAM. And so, historically, inside of all of your functions, all of those functions run with the editor role. We kind of have one identity, and they all get editor. So that means that if you screwed up your programming and maybe there are cases where someone uploaded a source code file and your function evaled it. Potentially, that function could now create virtual machines, or it can't change IAM roles, but it can build other resources or do things that it really shouldn't be doing. Right? All our function needs is this concept of least privilege. Right? It needs to read from cloud, cloud storage to do a vision check, and then write to Cloud Firestore. So we have this concept of per function identities, and what that means is you can create a new service account and have that be given just the amount of privilege that it needs. And you can do that via custom roles in IAM or minting access tokens if you're accessing, say, the Google Drive or Google Sheets APIs. So we'll walk through that. So I have a function. It was called OCR receipt because that's what it does. It OCRs a receipt. And I'm going to create a new service account to represent the identity of that function. And then I'm going to create a custom role. And I'm going to call that role only the Cloud Vision and Firestore thing. And I'm going to pass it 2 permissions. And this is a little counterintuitive. Vision actually needs object get because we're pulling from GCS. And then the only permission that it needs to write to Firestore is, again, sort of confusingly, data store entities create. There's a bit of legacy there. But we've now gone from editor, where it could do anything in our project, modulo a few things, to exactly 2 permissions. And then we are going to actually grant that new role to our identity. And then we're going to redeploy our function with that identity. So now we've, again, gone from this incredibly overprivileged role down to exactly the 2 permissions that we need to read from Vision and storage and then write to Firestore. And then one of my other favorite things, so Vision, you may have noticed, doesn't actually have an IAM role. So it relies on OAuth scopes. And so you need this scope, for instance, the Cloud Vision scope. And so we'll give it the Cloud Vision scope, and it doesn't fit on the screen, but we'll give it the Cloud Storage scope as well, so it can go in right there. And we can use this cool thing called the metadata service. So the metadata server, metadata server, not service, basically is an HTTP server that kind of looks like it lives on your compute instances. And what it will do is it will fetch tokens for you. So when you deploy, right, like how many people, and be totally frank with me, like how many people have uploaded a service account to their compute? Just like, or like occasionally you upload it to GitHub because you screw up. I've done it, it's terrible. Yeah, I see a couple hands on that. Yeah, that's not great development practice, right? Because maybe your private repo becomes public, or somehow those credentials leak. The point of the metadata service is that you don't have to ever deal with credentials. You can just say, hey, metadata service, give me a token, and we refresh those tokens every half hour or an hour, so you're not touching credentials at all. You can just say, this is my identity, give me a token for the identity. And so that's what we're doing here. And we're actually even saying, give me a token that's scoped only to the 2 or 3 services that I need. And I can make that request, get the token, and then do my calls. And under the hood, our client libraries are doing this for you. I just wanted to be very explicit. Hey, this is a really cool functionality, a piece of functionality that we've provided actually just recently. OK. So we've kind of gone through half of our flow, where we've been able to securely upload a file and then run some things as admin securely before writing back to Cloud Firestore. So the storage rules that we wrote, I would categorize as pretty simplistic. If you've ever written Cloud Firestore rules, they're a little trickier. So we're going to go through some similar concepts and then see kind of how we extend that into the future. So as I mentioned, and this is going to be kind of a slight point of difference, that write that we did from the function happened as an administrator, which means that actually a bunch of these rules are not enforced, right? Because we go through IAM, and we do an IAM check that says, hey, your function is running kind of as an administrator. Let's check there. This is mostly, the Firebase rules are mostly for your end users, and they're kind of designed purposefully for that. But I'm going to go through an exercise of, we also want to ensure that maybe there is a category of user who is writing their expenses directly to the database. Maybe we have a mode in our app that you don't have a receipt and you just have to put in the amount manually. We still want to provide for that, so we would have to kind of write that schema out in our database. And also, it's just good practice to see people walk through this. So we'll start off with kind of a similar set of constructs that we had earlier. Right? You have a service, in this case it's Firestore, and you have that kind of similar boilerplate path of databases, documents, etc. For those of you who haven't used Firestore, it's a document collection database. So you have collections, for instance, expenses, and then a document named the expense ID, so expense.jpg or whatever. And we're going to say we actually care a lot more about schema validation. So imagine we kind of did the authentication check, and we did a if the user can do whatever. We want to validate, for instance, that unlike just the file name, like we have in storage, maybe our documents have to have certain properties. So in this case, we're actually going to write 3 properties: the image URL, so we could pull down our file and display it in the app; the amount of money; and then the user ID of the user that actually wrote it. And so the first thing that we did was we basically said, this document can only have those properties. That's what that has only check is. And the next thing that we're going to do is we're actually going to type check those. We're going to say, okay, the image has to be a string, because it's just a URL out to storage. The amount has to be a number, and the UID also has to be a string. It's just a Firebase auth UID. So we've done just simple schema validation, but then we can do some more complicated things. We can say, for instance, the image URL has to match a certain regular expression. So only allow them to store images that are stored in cloud storage for Firebase. Or maybe we don't allow receipt expenses over $1,000, right? We're like, whoa, you shouldn't be doing that in our mobile app, so we're going to limit that. And the last one that we want to do is kind of that quick auth check of the user who's writing this document has to actually be that user, right? I don't want to impersonate you. I don't want you changing my document later, etc. And then if we wanted to, kind of for completeness, we could say things like allow update, allow delete, etc. If a rule is not specified, everything fails closed, right? That's how this whole thing works. So don't worry, your entire database is not public on the internet unless you do something like, say, allow reads and writes everywhere, which, that is an option when you start in test mode. You can say, yes, allow everything to be public on the internet because it's really fast to iterate. Not great development practice. And I'll get into some ways that we can help kind of make that easier in the future. But there's another tool, right? If you're looking at that and you're going, oh God, I have model classes with 15 or 20 different properties and I'm storing them in Firestore. This is going to get crazy to do that all manually. Do we have the tool for you? So I always feel kind of funny. I work at Google. I've worked at Google for a while. Has anyone heard of protocol buffers? A couple people? Okay, it's a Google conference. I guess it kind of makes sense. So protocol buffers are basically a way of defining a schema independent of a programming language. So it's an interface definition language. So I can define an expense proto. And I can say, hey, that has a string, image URL, an amount of money, and a UID. Those fields are all required. Maybe actually, I should have made image URL optional because, maybe we have people typing in expenses manually. But you can actually generate a bunch of things from that. For instance, you can generate all of your classes for your model objects. So for instance, it would create expense.java. And it would create, expense.swift and TypeScript and whatever other languages. And we've extended it to also create rules to validate those model objects, right? So what happens here is your flow is you define your objects in protocol buffers, and then it generates the model objects on your client as well as the rules on your server to validate those model objects. So if you're always deploying those things in sync, you should never get to a point where things are kind of egregiously broken in your data model because you should never be writing those things. So definitely check that out. It's just kind of an open source tool. You can run it yourself, and it will generate all of the various model objects that you want, as well as rules to validate them. And that makes it a little easier, right? Because now you just say, oh, is this an expense? And pass it in. And it's like, yes or no, it's an expense. You still have to include whatever kind of other business logic checks you have. We're actually investigating. Imagine if we go back, and instead of just saying what they are, imagine if you could specify conditions in a proto as well to say, hey, this value has to be between $0 and $1,000 in amount. And then we could kind of automatically do that as well. So there are some kind of interesting ways for improvement. The other one, just kind of going out on a limb, is actually going in the reverse and saying, you have a Java class, generate me rules off the Java class to validate it. Well, that's a little bit of a harder problem, but still something super interesting. And if anyone is looking for fun computer science problems, definitely build something, share it with us. We'd love to see it. Cool. So we talked through that example of a user writing some more complex data. Now we know that our users are going to be reading from our information. So we'll do a similar exercise. We'll say, great, users can read all their own expenses. Everyone should know what this looks like. We're just going to say, yep, you can get a single document, or you can query for all of your documents, assuming that your ID matches the ID in that document, right? Remember when we created things, we had to ensure that those are matched. We're going to do the same thing on queries. And so this would prevent me from querying someone else's data, which obviously we don't want. And that's where we get to the first gotcha. And this is why Firestore is a little interesting, right? So you can imagine that we have, in our expenses collection, 3 different expenses. And maybe we have more than that, but we'll start with 3. And there are 2 expenses by me, user 12345, for $10 and $3.99. And then some other user has, a $1.50 expense. So as you can see, that and then our other one is different. And so you might kind of natively expect that, hey, I have this set of rules that's saying, only give me my things. I'm in a query and, maybe I'm going to get only my documents. And that is not how things work, right? People get really tripped up here because Firestore is like, no, I can't feasibly give you only those things, right? Maybe there are only 3 items, but maybe there are 3 million items. And Firestore isn't going to look at every single document and be like, yes, Mike needs these 3 items. So you may kind of reformulate that and be like, I'm in development. All the documents are my own, right? I own every single one of them, and that's the only thing in the database. So you may do the same thing. You may say, hey, give me all those documents. They're all mine, right? And nope, Firestore still can't do that. And again, kind of what's happening is we have to know kind of beforehand if we can fulfill the request, right? So you actually have to say, hey, write a query that says, give me all of the documents where the UID is equal to, I hard-coded 1, 2, 3, 4, 5, but what I would do is I would pull my UID client-side off that token and then match that. And in that case, Firestore is basically asking this question, right? Can I prove that this operation will be allowed without ever looking at the data, right? Because if we had to look at 1 billion documents in order to return you 1 document, that would be an incredibly, incredibly slow database and an incredibly slow product, and that's not the promise of Firebase, and especially not Cloud Firestore, where we have to do tens or hundreds of milliseconds of sync time. And so the answer in that case is yes, we can, because you've provided information in the query that we match with the rules that you've written. So that's the concept that you kind of need to think about when you're writing Firestore rules, is we're validating it based on the rule and the query, not based on the underlying data. Okay, so I said that I'd come back to this. What about role-based access control, right? So we've been living in a world I won't go all the way back. But we've been living in a world with a bunch of different attribute checks, right? Of, ensure that the size is less than this and the UID matches this. But I think a lot of people conceptually think about things in role-based access control terms, right? You're like, I'm a user. Maybe I have a construction worker role, therefore I can access a toolbox, right? Like life just sort of kind of works this way. So RBAC, as opposed to ABAC, user, role, resource. And maybe there are cases, we've gotten a little more fancy in our application, and we work for a big enterprise, and they have admins who are checking our expenses, and we have to give the admins access to view our expenses to audit or whatever. And so we can write this little kind of local function and say, hey, if it's me, allow me to read it, or if this person accessing it is an admin. But how do we get to that kind of is admin check? We can do that in a couple ways. But the simplest is you can actually write this kind of little local function, isAdmin, and what it's going to do is it's actually going to look up data that is in the database. So you can create like access control lists in your database, or for instance, if you're building kind of like sharing information, if you're building a Google Docs or a Google Drive clone, you could say hey, these are all the people who have access to a document. In our case, we're just going to create another collection called admins, and hey, we're going to look up and say, is this user in the admins collection? And if they're in the admins collection, great, we'll allow them to be an admin. Which of course brings this amazing, interesting question of like, oh, well, how does someone get in the admins collection if doing so now grants them these magical powers? The 0th order answer is the one that I commonly do, is literally just go into the console and copy an ID and paste it in. But that's obviously not super scalable. So let's imagine that we're going to actually use another function, piece of functionality of Firebase Auth and our integrations, which are called custom token claims. So a custom claim is something like we have here of an isAdmin flag. And if we go all the way back to that first section on Firebase Auth, we talked about that token, and we talked about the body. And within that body, there are a bunch of kind of normal claims, like my email. And we can augment those with custom claims. So we could, for instance, when that token is being created, create it with this additional flag that says, this person is an admin, therefore they can do another set of things. So you might be like, oh man, that's awesome. I can put all sorts of information. I can put, the company that they work at. You can put, group information. You can store profile photos. Don't do that, actually. I had someone do a 10 megabyte profile photo. Turns out HTTP headers do not take well to 10 megabyte photos in the header. And so we've kind of provided a couple limits on that, right? So custom claims aren't kind of a panacea for all of your authentication needs. right? We limit them to a kilobyte, so you can only kind of put static data and like small amounts of static data. And also, we don't want them to be heavily dynamic, right? These things are refreshed, when the token gets refreshed, roughly once an hour. And so don't store information like the chat rooms that a user is allowed to access, because they'll still be able to access it for an hour, right? If you need small dynamic pieces of data, store that in something like Firestore in another collection, and do a lookup like we had with exists to actually look and see if that document exists. 2 shameless plugs. So Jen Person, one of the Firebase DAs, did a really good talk that dives all the way into use cases around custom claims, when you should use them and when you shouldn't. And then if you enjoyed the kind of data modeling perspective, yours truly gave a absolutely fantastic YouTube video, not biased at all, where we dive into kind of more complex examples. And then we also solve that bootstrapping problem of how does the first user get into a place. So we've written a bunch of code thus far. And I don't know about you. I know when I write my apps, I don't always test them. So I'm not going to ask people if they test their apps. But it's something that we all know that we should do, like brushing our teeth and flossing. And we're going to try and make it as easy as possible to do those things, right? So there are a couple ways that we provide to actually test that functionality out, right? I wrote a bunch of rules, and you're like, great, Mike, those look fine, but prove to me that they're actually secure. So that's what we're going to do now. So we provide the first tool, which is a simulator. And so a simulator is in our console. We allow you to, right where you edit those rules, actually test that those rules are doing what you think they're doing. So I've copied that exact same set of rules. Over on the left side of the screen, you can see, hey, we're going to try a create. And we can create a document. So I actually went to the taco trucks across the street, and so I don't have an expense for it. But imagine that cost me $10, and I took a photo of it. So the photo is stored over in storage, $10, my UID, remember that number, 12345. Great, I'm going to build that document. I'm going to go down to the authentication section, and I'm going to put my UID in there, 12345. And then I'm going to click run. And run is going to say, yep, your read or your create to expenses/lunch has all those keys, matches, is less than $1,000, etc. But if, for instance, I just change that Firebase UID to 13579, so basically not myself, but I'm trying to write a document that has that, it's going to fail that write, and that's obviously by design. And the same would happen if I say, change the expense to $2,000 or similar. It would kind of give me that nice failure message of, hey, something's wrong. So it's a really nice way of doing that. If I drop the simulator down, it'll also provide a total version history, right? So every time I save and redeploy those rules, I'll have a version history. So I can kind of test that as I want. And then if something broke, I could, for instance, kind of, one-click roll back in the simulator, hey, get back to a safe state. But obviously, that's kind of nice for these one-off things. But ideally, when you're developing, you have a little bit, you have unit tests or an integration test. So we also provide a local emulator. And so the local emulator will basically allow you to programmatically do those similar tests. So you'd have your rules, and you have kind of your local database. You can read and write to it. And I can create, hey, in my expenses collection, maybe I want to go and fetch your expense versus my expense. And I've written rules that kind of do that. And then I can write assertions and say, hey, this test should fail under this set of circumstances, but maybe this test should succeed. And then I can validate those. So that's a really nice way of, again, getting more towards the automation of your security. Awesome. So we've talked a lot about kind of the deep technical aspects of how to secure your application. But there are a lot of things that actually I think are more common and more frequently done incorrectly that are much bigger security vulnerabilities. So I'm doing another talk tomorrow, shameless plug number 3, I guess, that goes really in depth on kind of threat models and threat environments. But basically the idea is there are threats in the world. Everything from the random people on the internet pinging your website to state-sponsored entities who are doing very targeted and specific attacks. And so in the category of threats, right, when you build an application, you want to kind of pick the threats that are most likely because those are obviously, they're more likely to occur, therefore you should kind of try and solve them initially. Unless, again, it depends on what you're doing, but generally understanding kind of the, what threats are out there, what tools may be used to break your application or have malicious things. One of the most common ones, and I think we call it sort of insider risk or unintentionally malicious behavior, is everyone is really worried about this guy, right? The hacker who's sitting around trying to break into your app. But like, practically speaking, it's like this guy from IT who like accidentally deleted everything. Like, that's a much bigger threat than this thing, right? Like, much lower probability, maybe a little more dangerous, but practically speaking, if this is going to happen 98% of the time because they clicked the wrong button, that is still a really big threat that you want to deal with. So, this Mike at McDonald.com guy, we don't know if we can trust him. I wanted to add him to my project. And typically, my alter ego is an editor, right? Or is an owner. I can do anything in this project. But maybe I don't really trust this other one. And so I want to give him kind of more specific permissions. I don't want to give him full access to, say, all of my business data or access to send push notifications. I want to say, hey, Mike, I'm going to give you a particular role. And we can actually go and say, okay, there are some analytics roles that are reader or writer. There's maybe a developer role. And Mike is going to be doing some development work for me, so I'll give him the developer admin role. So he can go and delete the entire database, but he can't send push notifications to spam all of my users, right? So there's some guide rails there. And if you need, you can kind of bump out of that into Google Cloud Platform and use the custom roles in Google Cloud Platform to create, similar to what we did for our IAM example, give Mike at McDonald.com only access to a database, and maybe even only read access to a database and write access to storage. You can kind of create whatever you want and give them that custom role, and the Firebase console will respect that. Cool. And the last one, again, kind of going a little more abstract, but developer experience is a really, really important part of security, right? Because if your processes are really cumbersome, right, if you have a bunch of manual steps, people are going to kind of bypass them or take shortcuts and end up in places where you've kind of unintentionally built vulnerabilities into your application. And there are a couple common ones that we see really, really often. Shared environments is a huge one, right? So for those of you who are running Firebase apps today, you may have things like your dev and your beta and your prod apps all in the same project. And that means they're sharing an auth database. That means they're sharing an actual database. That means your metrics are kind of looking interesting. Projects are kind of a nice firewall between those, right? Because you want an entirely separate database that, if someone comes along and accidentally deletes it, that's fine, right? It was staging, you can rebuild it. And so really, really recommend that. And I think there are a lot of people who say, oh man, it's really hard to set up environments because it requires a lot of manual toil of enabling all of your APIs, et cetera. So tools like Terraform or Deployment Manager will help you kind of build that infrastructure. So the infrastructure as a code type thing will help you do that easier. And related to that, right, like if you have a very manual tool chain, a lot of times, people will do things like, they have, for building an iOS app, have like the one Mac Mini in the corner of the office where like build the app on and then, put a thumb drive in and take the IPA file off and walk it over to another computer to upload it to iTunes Connect. Like, that's a really bad experience, and you're likely to, copy the wrong file or do something like that. And so CI or CD tools, so using Cloud Build, or we have a really great mobile tool called Fastlane, which does things like automate, provisioning profile signing and upload to the App Store, and kind of doing that, securely. So not everyone at your company can say upload an APK to the App Store. Only, the Cloud Build deployment agent can do that. You can kind of build some additional security in there. Okay, so that is all I have. I have about 10 minutes. If you have questions, I am happy to answer them. And I will stick around after as well. Otherwise, please submit your feedback. And if you have other questions, I'm on Twitter at ASCIIMike, ASCIIMIKE, and would love to help you wherever you are in your development journey. Also, if you've built awesome Firebase apps, send them my way. Send them to Firebase on Twitter, right into support. Again, I love seeing what you build, and I may try and break it and give you feedback on that. So thank you all very much for coming, and enjoy the rest of Next. If you do have questions, feel free to come up to a microphone. Oh, yes. Feel free to shout as well, and I'll try and repeat it. Yes, so the question was, is there any way to encrypt a specific field in Firestore? So broadly, there are kind of two categories, or two primary ways of doing encryption when we think about it. The first is customer-managed encryption, and then the other one would be customer-supplied encryption. And so customer-managed encryption would be, for instance, certain products let you provide a cloud KMS key, and then we'll just kind of transparently encrypt with that key, but everything you get in and out is already decrypted. There's another one which is customer-supplied keys, which is basically application-level encryption. And so you would provide a key, and then maybe we would encrypt it. So like GCS does this, where you can provide a key for a GCS object. It will do the encryption in memory, throw the key away, and then when you want to fetch it, you have to give it the key back. Or actually what you do is you just get the encrypted object and decrypt it locally. The short answer is I have coworkers downstairs who have done like PGP encryption, but it ends up being application specific. We do. So the question was, is there anything wrong with storing keys in the claims? I wouldn't, because those claims are not encrypted. Right? A JSON Web Token is base64 encoded, so anyone could pull that apart. I think the better answer would be, if you're on a mobile device, essentially you would generate a public-private key pair and store it in the keychain. And so, again, I have a coworker who did this with PGP keys. And so you'd create a PGP key pair, and then you would do encryption based on that. And you can store the public keys in something like Firestore, but then every device needs to know that. It gets a little more difficult when you want to do sharing with other people, but yeah, really good questions. Yes?
Hey, my question is, the examples you showed, you had a bunch of rules ANDed together, and I asked the same question in Dory, by the way, so you can ignore it there. But if any of those fail, it seems like you'll get a single response, and so you wouldn't necessarily know why it failed.
Yes, that is something that we are working on improving. Yes. Turns out we compile them down and lose some of that information along the way, but we do plan on providing more granular error messages. If you've used the real-time database, it will actually provide you this exact condition is what failed. So we are kind of backporting that functionality. Yeah, good question though. Any other questions? Comments, jokes, we're open to it. Yeah. Yeah. Okay. Yeah, so the question was about getting full snapshots of a document. So there's, sorry? Yes, so you would get, I'm trying to remember, so the way that it used to work in the real-time database world, so the Firebase real-time database, kind of the historic legacy product, giant JSON blob in the sky, and it's just kind of a tree of values. So you would subscribe to a location, and we would hand you everything below that. So we would give you kind of the entire subtree of below what you got. In Firestore, we changed that model slightly where we said, okay, things are now collection document hierarchies, and you can subscribe to a collection to get a particular document back. And so that document could be the expenses document. And maybe I did some kind of really inefficient things where I threw 50 values in there. It just kind of grew organically over time. There are a couple things. One, over the wire, we are not downloading the whole thing. So we're kind of doing diff sync of, hey, these values have changed, we'll do those. But it still surfaces as the whole object. And that's sort of from a, if you've done kind of like, if you've read Martin Fowler programming patterns, there's a programming pattern called CQRS, Command Query Response Separation, something like that. And it basically says, all of your communication should go back, to a database one way, and then send you the full change so you can just kind of rewrite your thing. So if you've done reactive programming, or if you do React, it feels very similar of like paint the whole thing, given the whole piece of data. But we recognize that kind of over time things may grow organically. So we typically say, okay, break some of that data out into subcollections. Well, I guess the higher level one is all of these databases are NoSQL databases, right? So everyone, when you go through databases 101, the answer is like normalize everything, right? Like don't have duplicate data, right? Try and do everything through joins. Yeah, great, that works for a SQL world. When you go to NoSQL, suddenly you're making a different set of trade-offs, right? And suddenly denormalization becomes totally feasible to say, okay, we're going to just replicate data everywhere because this collection is a view for this this actual view, and this one is for a different one. So you can start pulling data apart that way, which is probably what I'd recommend. And you can do that either into kind of a sibling collection, or for certain things, there are cases where subcollections make sense. And things like, there are a couple features like collection group queries, where you could then say, give me all the expenses and profiles related to a user ID. So kind of get some disjoint information. Things like that are coming. But in general, yeah, like don't be afraid of denormalizing data. It may not look efficient, but it's a set of trade-offs that you're making that NoSQL databases, at least in Firestore and those, are very good at making. Yeah, awesome question. Anyone else? Otherwise, you don't have to stay the whole time. I'm happy to get off the stage. Otherwise, we have 3 minutes. I'm happy to talk at the front as well if people have questions. But I'll vacate the stage now. Thank you all very much for coming.
Let's build a house. We'll have a backyard. Something beautiful, something with a view. Let's build a house just for me and you. I'm coming.
I think we're going to wait just a minute or two more so that all the folks that were waiting in the standby line can find a seat, and then we'll get started. All right, I think it's starting to slow down, so why don't we go ahead and get started. Welcome everybody to HYB 102, Incrementally Adopting Istio. My name is Sundip Parikh. Unfortunately, my co-presenter Tahir couldn't be here today. He ended up not getting his passport with his visa back in time to make it all the way here from Singapore, so he couldn't make it, but he was very upset about it. He had a lot of good stuff to share, so we're gonna find another way for him to get some of the slides that he was gonna present back out to y'all at another time. So today we're going to cover the what, the why, and the how of Istio. Due to scheduling, I think this session would have been better served earlier on Tuesday, before a lot of the other service mesh and Istio sessions that kicked off, but I don't make the rules on that, so we'll have to go talk to people in marketing about that later on. So this is coming sort of in the middle of some of the 200 level stuff, and some of the 300 level things are still happening tomorrow as well. But just for my own, actually, education, I'd love to know how many of you, by a show of hands, have used Istio or played with Istio at all? Oh, shit, that's a big number. What about Istio in production? Who's got Istio in production? Okay, awesome, very cool. By the way, I hope you all saw who raised their hands so you can go talk to them if you've got questions after the talk is over. All right, so just a quick little bit about me. I'm a developer advocate or a cloud native advocate. The title changes all the time for Google Cloud. And before Google, I worked at MongoDB and Apple and a bunch of other random startups. You can find me on Twitter or at GitHub with the same username. People always ask, it's Circus Monkey minus the vowels. And the content that I'm going to talk about today is up in a repo there as well, and I'll have the link at the end, so you guys can pull that down. I'm going to do a little bit of slides and just a little bit of demo at the end, but all the material is actually like a fully baked set of tutorials you can walk through. All right, So let's start with why Istio, right? We've just finished kind of getting into Kubernetes and be comfortable there, and now we're going to add another layer of abstraction on top of it. Why do we want to do this, right? Why is Istio so critically useful and important to deployments? Right? We have containers. Containers are great. We love containers, right? It lets us be really portable and get out of this whole, like, it worked on my machine, but not over there in production. So we can get this sort of unified environment, get this great packaging. Containers, awesome. Kubernetes, also great, right? It does a lot of great things for us. It orchestrates those containers really well. It lets us schedule them out and bin pack them very tightly into a cluster. Really powerful. But microservices deployments are hard by their just very nature, right? You have a bunch of services strewn across a cluster. Teams are iterating at different paces. You've got dependencies you don't even know about, right? Again, spread out across this whole thing. Applying policy, applying control is challenging in that environment, right? Istio helps us get from that sort of mess on the left to something that's more organized and functional on the right. If you think about some of the, again, that higher level of abstraction, right? So we've moved on from just containers and pods and scheduling them and deploying them into a cluster. But again, if you think about that next level up, what makes those microservices deployments hard, right? So a good example is canary releases or doing blue-green or traffic splitting. If you want to do that in Kubernetes today, you actually have to run the correct ratio of pods. So if you want to do something like a 90-10 split to test out V1 versus V2, you'd actually have to run 9 pods of V1 and 1 pod of V2 to make sure you've got that 90-10 split. That's kind of a pain. It requires a little too much hand-holding to really work well. You don't really know who you're talking to, right? Your services could have a person in the middle or a service in the middle there, or you could be opening yourself up to some kind of attack or injection, right? You want to make sure that services know who they're communicating with back and forth. You want to be able to quickly dig into high latency drivers. Again, if you think of a microservices deployment, you may have a web request that comes in the front end, but it may travel around to a number of other services. Well, how do you know if it's slow, right? The end user might feel like, well, this is taking 500 milliseconds or over 1,000 milliseconds, but it might not be the front end. It might be one of the various backends that front end is talking to. And there's a whole host of other things, right? Like digging into L7 attributes, like request headers. We can't do that right out of the box in Kubernetes. You can't really control who accesses services, and you can't track requests from start to finish. So you don't have a level of visibility to match, again, the complexity of the deployment you're doing. So that's a little bit of why we think Istio is really powerful, because it gives you access to all these. So again, we've talked about service mesh. Many of you obviously have played with Istio, so you have some understanding here. But I like to start with this idea of what is Istio, right? Istio, if you think of it in any, if you boil it down to its kind of simplest concept, Istio is about automation, right? It goes beyond, I think, what just a sort of a service mesh. I don't think that really encapsulates it. Istio gives you this power to apply policy and control to your entire deployment, whether it's 5 services or 500 services. You can take a single rule and say, I want to turn on MTLS and make every service mutually authenticate to each other with one rule, and that goes cluster-wide, right, or namespace-wide, depending on how you roll it out. So the 3 things that Istio kind of gives you around in those areas of automation are, 1, very uniform observability, right, metrics, logging, tracing, right out of the box. Operational agility, which is a fancy way of saying, I think, a lot of traffic and networking control. And then a very deterministic, policy-driven security model. So if you dig in a little bit further, with telemetry, you can examine all of that traffic in and out of those services and in and out of your cluster as well, with very little to no instrumentation in many cases. Right? That's incredibly powerful. You could take the responsibility of adding in things like latency and tracing outside of the hands of developers and say, you don't have to worry about instrumenting this as a starting point. We'll learn a lot just by putting this thing and running it with Istio. Same thing is true of traffic. You can take the networking control outside of the application, make that a loosely coupled structure. So applications can be deployed however they need to be, or services can be deployed in whatever way makes sense, but then the cluster operator can decide how traffic splitting should happen, how rollouts should happen. And then finally, security, obviously, right? Being able to secure access and communication between services or add authentication policies to individual services, or all of them, depending on how you want to roll it out. So at a glance, Istio is, again, it does add complexity, right? We're sort of solving complexity by adding some other complexity. So that's a little bit of a trade-off in terms of how much has to happen. But if you think about it, what you're effectively trying to do is, one, narrow the problem space a little bit. You're trying to tell your application teams, take the complexity away from them. You're saying, don't worry about networking control. Don't worry about some of the telemetry aspects. Don't worry about security. We'll take that complexity away from them, and we'll put it on the cluster operator, but then we'll give them, again, that automation to apply those things in a much more granular way and be able to, again, incrementally roll it out. So if you start with the most basic component, that's the Istio sidecar proxy. And you'll see that little hexagon over there. That's actually the Envoy logo. So the Istio sidecar is powered by Envoy, right? It's effectively the Envoy proxy. Envoy is a fantastic project, fantastic piece of code. It's very high performant. And because it lives in your pod right alongside your application container or your services container, they share the same network space, which means it can actually capture and filter through all the traffic going in and out. So it adds a thin little layer of control over the traffic going in and out of your containers. The next part is, I guess, what we call the sort of the data plane, right? Which things are sort of generating and pushing data out or implementing rules. Again, that's the Envoy proxy piece itself, but when you kind of slice across your cluster, we consider those proxies as the quote-unquote data plane in the cluster. And this is something you can deploy today. You can take the Envoy open source proxy and deploy it as part of your containers or part of your pods today. What's missing is a central control plane to deliver rules and configuration to those proxies. And that's really what Istio provides. It kind of packages this whole thing up and gives you a unified control plane with a series of components to push rules and configuration information out. And so inside that control plane, there's three main components, right? And there's actually a fourth one I didn't mention here, Galley, which is responsible for handling some of the configuration components. But the three main ones that we tend to deal with on a regular basis are Pilot, Mixer, and Citadel. So Pilot's responsibility is taking in the rules that you give it and making sure they get back out to all those proxies. So at any point in the lifetime of your cluster or your deployment, you can see all of your pods and the rules that Pilot has sent out and figure out which ones have synced and which ones haven't, which ones have gotten the latest version of the rules, which ones haven't. So you have that control there. Mixer's job is to take metrics and telemetry data that come out of those proxies and then send them downstream to the telemetry backend of your choice, whether it's Prometheus, Grafana, Stackdriver, you name it. And the last one, Citadel, is responsible for managing certificates. So its job is to make sure everybody's got the right certificates and keys and authentication information, and it does the magic of rotating those things around all on its own. So that's a little bit of the components of Istio, but what does Istio really do for you, right? If we get into some of that detail. So if we start with observability, or observing, as I mentioned, you get automatic tracing, logging, and monitoring by default. So as long as you send your logs out to localhost, as long as you publish your metrics in known good endpoints, and whether you do or you don't actually add any tracing information, it can actually still deliver some tracing information out from your applications. So those proxies, they send that tracing and that telemetry data to Mixer, and Mixer has a well-formed adapter API that lets it send all that data to particular backends. And you could, again, split these out. So you may say, well, if I'm running in GKE inside of Google Cloud, maybe I want to use Stackdriver logging and Stackdriver trace, but you really love Prometheus and Grafana, by all means, you can put those two together. So you could have that mix of different backends and components depending on the piece you want. You could even have it so you push metrics to Prometheus and to Stackdriver if you wanted to. There's no real limit to how you can configure this. For connecting services, right, that kind of operational agility component is really where the networking piece comes in. There's a few objects that are really dedicated specifically to networking inside of Istio, and those are virtual services, destination rules, gateways, and service entries. And so those, in some combination of one or more of those, they let you do things like traffic splitting, traffic steering, right, from one version to another, fault injection, circuit breaking, and egress control, which is really powerful, right? If you have a lot of services that call external APIs, this is a really powerful way to put some control over that. But more importantly, as a security mechanism or to form a better security posture, let's say you have a bad Docker image that you pulled and deployed, maybe a malformed tag or maybe something got injected into that container. Well, if you lock down egress control, that means nobody can make outbound API calls or outbound calls unless you've specifically allowed that service. So now you're getting just sort of this free kind of perimeter around your deployment just by having that proxy and having this infrastructure in place. If we dig in a little bit to some of the traffic splitting and traffic steering, the way the Envoy proxy works is you send rules up to Pilot in that configuration. Pilot sends those rules to those individual proxies. So now those proxies themselves know how to route traffic around from one to the other. So in the top example, we've got service A and service B. Service B has different versions that it might have. If you just rely on Kubernetes routing, you get round-robin routing, right? So you basically get an equivalent amount of requests spread across here. So in the example, in the right side, in the upper right there example, you might see like 25% going to each pod. With Istio, we can actually control this and say, well, we want 95 and 5. We want to have a canary version that we roll out very slowly. On the bottom example, that's really where we get into things like traffic steering. Again, because of the way Envoy works, it can actually inspect the headers coming in to your applications. So that means we can actually say, based on maybe a header value, I might want to direct traffic to a particular version or a particular pod. So for example, you could say, hey, for logged in users running on iOS with WebKit version XYZ, direct them to this canary rollout test or to this other version of that service. So you have that level of control that you didn't have just, again, with sort of vanilla Kubernetes. And as I mentioned earlier, you can also inject things along the way. And these are really not necessarily things you're going to use in a production environment, but from more of like a testing and resiliency perspective. You may want to inject things like delay, sort of retries, or even other connection rules. Circuit breaking is a good example. You can inject a circuit breaker inside of this path between services and control, whether you want cascade failures to happen or if requests start to fail, just cut off access immediately. So you're not seeing, your end users aren't seeing sort of high latency waiting for errors to time out all the way through. And as with a lot of the way Istio works, those rules can match very particular conditions and be directed at a percentage of requests, not all requests or just some. So you have, again, very granular control that you can really implement across your platform. On the security front, 4 main components that really stand out, right? Encrypting traffic between services, authenticating services or service authentication, service to service, I should say, auditing control, and access control policies, right? Again, very powerful stuff. Think of it this way. I can implement, again, mutual TLS is a good example, and actually one that a customer came to us with. They were told by one of their downstream customers that they needed to encrypt traffic between all services, and Istio was the fastest way for them to get there because they redeployed their pods with the sidecar proxy and then flipped a bit with one rule to turn on mutual authentication across everything there. And that's really powerful. The security model, this diagram's a little bit hard to read in a few spots. The point is it's kind of rolling together all of the security parts of the infrastructure that you can kind of inject along the way. So requests are coming in on the far left and sort of traversing through to the far right on the egress side. And you can see where Citadel's issuing certificates, where things like service authentication, maybe with JWT tokens or MTLS between services is happening. So you have, again, this level of control that's not really possible without another higher level tool. So that's a little bit of the background of the why and sort of the what of Istio. But how do you put Istio to work for yourself, right? And this is where I want to get to this idea of incrementally rolling it out. Because like with any new technology, you don't really want to start and go from 0 to 100% on day one. You want to find the features that make the most sense and then start rolling those out bit by bit. So the easiest way to get started with Istio is actually we built something inside of Google Kubernetes Engine a little add-on that lets you deploy Istio by default, or along with your cluster deployment. So using either gcloud or the Cloud Console, you can actually spin up a Kubernetes cluster, and there's a little section called add-ons, and just check the box for Istio, and then pick a security approach, whether you want permissive or strict. And for the purposes of this example, I used MTLS permissive just to make things a little bit easier. But that's something I started with here. So this is an easy way to get Istio. But frankly, installing the OSS version is not that terribly challenging either, right? Grab the latest release, apply it via the Helm chart, and you're off and running. And with the Helm chart, you get the level of customizability you might want. So for example, maybe you decide today, I only really care about telemetry. Only get the components that worry about telemetry. Don't worry about having the traffic components or the security components. You can always upgrade to that later on using Helm. So Helm gives you that power and flexibility. And there's also a quick start inside the Istio repo as well that just deploys everything. So you have a couple of different options for how to get the software running inside of your cluster. Once you do this, and once this cluster comes up, you end up with a bunch of pods running inside the Istio system namespace. And again, it's all those things we saw earlier: Pilot, Citadel, Galley, among other things like, depending on which version you installed, OSS, or whether you're using the one we package here for you. If you use this version, we install all the stack driver adapters for you by default. If you use OSS, it comes with Prometheus and Grafana out of the box. So you have a couple different options there. But once you've got this up and running, once the system is ready, you can actually start to include the sidecar proxy inside of your pods. And there's two ways to do it. The bottom way is the way we see a lot of folks do it, which is basically taking a namespace and saying, anything that gets deployed to that namespace, by default, just auto-inject the sidecar proxy. Or you have the other approach of saying, well, I'm going to do it on a per sort of YAML basis. Every time I push a new service, I'm going to filter my YAML through this Istio control binary that adds in the appropriate piece to your pod spec. So it includes the sidecar proxy. So there's a couple different ways to kind of get started there. But if you're rolling it out, what I would say is don't start with auto-injection, right? You don't want the pod out right yet. Again, it really comes down to the features that you're most interested in. The other thing I would also say, and I mentioned this a little bit earlier, is start with permissive MTLS. You can always turn it on later, but when you first turn it on, if you go with strict, it might start to break things, so you might want to roll it out, again, on a case-by-case or service-by-service basis. So that's just a little bit of getting started. Let's go through a few example kind of incremental rollouts, right? And again, think of the state of the cluster as, we've got Istio up and running, we're not auto-injecting the sidecar proxy yet. So for traffic management, let's say you've got a simple deployment here. And I wrote a little sample app called Weather Info because I was getting really tired of the built-in book info. I just decided to make another one. And it's got a front end and two different back ends, right? This just pulls the weather from an external API. V1 pulls it from a single city, and V2 pulls it for 4 cities and just displays it out. So nothing fancy. But let's say we want to roll this out in a way, again, using Istio incrementally, but we still want to take advantage of some of the traffic features that are available. So how do we do that? Right? Quick recap on traffic splitting, just to remind y'all. Right? We have this approach where we want to try to get this 95.5. Now, the difference here is that all of these examples, they've got the sidecar proxy in them. So the question is, and this is the question I asked myself about 6 months ago, how can I do this kind of traffic splitting without having to roll the sidecar proxy out? It turns out there's a little bit of a cheat and a way to do it. It's not necessarily the way I would recommend for everything, especially for full-blown kind of large-scale production deployments, but as you're testing things out and getting acquainted with the rules and infrastructure, kind of play with the networking APIs before, again, you go wide with it. So what we're trying to try to do here, our goal is to get to 90-10. And remember, without Istio, right, without anything by default, Kubernetes will just do round-robin 50-50 across both of these. So that's where we're starting from. We're starting from 50-50. Now this little box there is Istio, right? And I've got a little ingress gateway that's allowing inbound traffic at the top. So for us to get to this, there's a few components we have to deploy to make it work. So using a virtual service and a destination rule, we can actually direct traffic from weather front end to weather back end V1 at 90% and V2 at 10% by directing traffic through the ingress gateway. So again, rolling it out a little bit slowly, but getting a chance to test this out in a kind of a measured approach. So the traffic policy we want to do for this is, the first thing we do is create a destination rule. And as you can imagine by the name, a destination rule kind of tells inbound traffic where to go. So it's saying, I want to direct traffic to these possible, imagine by the name, a destination rule kind of tells inbound traffic where to go. So it's saying, I want to direct traffic to these possible subsets. So in this example, all the destination rule is really saying is, create some subsets of my service. In this case, single and multiple is what I called them. Right? So we've got a subset for single and a subset for multiple. I just want to have those on record as being things I can direct traffic to later on. And then we create the gateway component. We connect the gateway to the rest of the infrastructure. So what we're saying here is we're going to open up a port 80 on the gateway. We're going to do it for all hosts. Again, this is just a demo example. I wouldn't do this in real world. I wouldn't do this in production. All we're telling it here is we're going to set up a gateway connected to the Istio ingress gateway that comes with Istio by default, which is just another Envoy proxy, and we're going to tell it to open up port 80. And then we can actually create a virtual service that tells requests when they get to the ingress gateway where to direct them to. So remember, we had those named subsets of single and multiple a couple of slides back. So here we can call it out specifically. We attach this virtual service to that gateway we just created. We match on a very particular endpoint, in this case, /API/weather, and then we tell it to just traffic split those two across the single version and the multiple version at a 90-10 split. So that's it, we're done. Any traffic coming in through that ingress gateway is now going to go across those two subsets. So that's good, we've solved some of the basic traffic splitting problem, but we haven't actually connected the weather front-end component to it yet. So the last step in that process is to update the deployment. Excuse me. All we're changing here is we're changing the back-end location. And so this is actually in the weather front-end deployment spec for my piece, for the component that's running in Kubernetes. All I did is change the host name of where it's supposed to send traffic to. Now it's going to send it through the Istio ingress gateway instead. So really the only service that had to change here, that had to be redeployed, if you will, was the weather front-end component. Once you push this out, all the traffic will now start to go through that other piece, the ingress gateway, and then it'll get split there. So we did this without deploying any Envoy proxies across those pods that were there. Again, the nice way to do this is, or the nice thing about this is that you're not having to redeploy or update infrastructure. You're not having to inject the sidecar quite yet. And it's a good way to sort of test and get familiarity with the components, with the APIs that are available to you. But that's one example of just kind of rolling it out. What about security? How do you roll out security in a measured and controlled manner? So in this case, we are going to have injection turn on because really, at the end of the day, for you to make use of any security infrastructure, you've got to have the sidecar proxy included in those pods to enforce those policies. So here, what we did is we've got two namespaces in our cluster. One I called legacy, which is some vanilla service, and one called secure. And in the secure namespace, I have Istio auto injection turned on. So that means when I deployed weather front end, weather back end, they got the Envoy proxy in those pods. So now what we want to do is we want to slowly roll out MTLS. We want to roll it out so we secure the infrastructure in the secure namespace, and we want to allow traffic from the legacy namespace. So the first thing we do after we get these services up and running is start with a security policy. And for those of you that are paying really close attention, I had to shorten the names of the API versions to fit on the slide. So if you happen to look at these later on, don't copy from here, copy from the GitHub repo. That actually has the correct YAML specified there. But here what we did is we are setting an MTLS, we're setting up the backend service. We're turning on a policy there for security. We're saying we want it to have a permissive policy so that anybody can connect to it from within that cluster. So the net effect is that this service now has access to connect here, right? So now it has a permissive policy you can connect, and weather front end was not impacted by this. It was because it's got the Envoy proxy already, it can already connect to it. And now what we can do is apply a destination rule that's saying anybody that's got the proxy as part of their pod can use mutual authentication. So what this is doing is, again, slowly rolling out MTLS to all the services that can take advantage of it. So this destination rule, all it says is use the Istio mutual mode. That means if you are capable of doing MTLS, let's go ahead and do it. So the net effect there is that now we've got mutual TLS happening between front end and back end, but still maintaining permissive access to weather back end. By the way, and that rule was kind of underspecified, right? I left it a little bit open about who could connect to it. You can actually get way more fine-grained and say only certain services can utilize that permissive mode. So you have that ability to control at a very fine-grained level about who can access that thing without using mutual authentication. But now what were to happen if we turn on strict, right? If we take it from a permissive mode or mutual mode to strict, right? Once we implement this policy and update that policy from saying permissive to strict, that means anybody that doesn't have the proxy, that can't do MTLS, won't be able to connect to this. Because what they're missing are the certificates from things like Citadel and the configuration from Galley to make it work. So this is an easy way to start with, right? Again, remember the cluster we deployed was set to permissive mode. So that was already kind of an open setup. But with mutual, we are actually able to turn on MTLS again on that service by service basis. Anybody that could do it would use it. And then once we transition to strict, we cut off access to legacy clients. So this is a good way to think about, again, it's a demo and I couldn't fit that much information on a slide, but think about how you might, again, slowly roll this kind of thing out across a larger environment, right? If you map this kind of problem to 500, 1,000 services, it's an easy way to enforce policy and enforce security very quickly and to start encrypting traffic between services immediately. So that was an incremental rollout of security. What about telemetry, right? This is another, I think, key feature of Istio where, again, you get that monitoring and that tracing and logging for free. I mentioned this a little bit earlier, but I love hitting it as much as I can. Without additional instrumentation, you get this output directed to your choice of backend. So what are some of the metrics that you get by default, that you get for free? So you get things like request count, request duration. Particularly for HTTP, you get things like size of request body, the response body size, and then for TCP services, you get additional information like bytes sent, bytes received. And this is actually for source and destination as well, so you get variations for both. So you can actually track, again, traffic inbound to your pod, traffic outbound, and control and understand the telemetry and what's happening there. So these metrics just start getting published, and again, in open source Istio, they go straight to Prometheus. In the version that you can install directly through the GKE console, they go straight to Stackdriver. That's it. So at this point, what I'd like to do is switch to the demo. Can everybody read that okay, or is that big enough? All right, no one said no. So let's see, I'm gonna make sure we're on the right cluster here. So I'm in my hybrid 102 cluster, and we can show you what's running on here. So I've got that example app I talked about before, the weather front end with weather backend single, weather backend multiple, and I got a little load generator script that's generating and pushing traffic through. And so what I wanted to show you first is the Stackdriver trace component. So this is, again, I didn't change anything in my code. I didn't instrument. I didn't add anything to it. All I did is turned on Istio, deployed those containers with the sidecar proxy auto-injected, and then it started sending data to Stackdriver trace immediately. And so I just did this earlier today, so that it doesn't have an automatic report there, but we can actually dig in a little bit further. So this is the Stackdriver trace UI. It'll, by default, give you things like insights over the last 7 days, or it'll create some auto-analysis reports for you, or you can actually just dig into individual URLs or requests yourself. So if I go over here to the trace list, I can actually look and see, I can look at the latency of the requests that are coming in. Again, everything's being generated by that load generator script right now. But actually drag along here and figure out, so let's pick this little section there. I had a couple of high requests. So I can look here and say I've got a request that was 301 milliseconds. If I dig into that one completely, one, I get this timeline, so I can see again the request and how long it took. And then over here on the right, I get a lot more detail about things like the timestamp, and then I get to see things like where it came from. And I think that's where it's really important. I can actually go here and say the source workload was weather front end, right? The URL was API weather. This agent that's using the track is the agent that's built into the sidecar proxy, or built into Mixer, I should say, and where that traffic was going. So we get some level of detail here. I can also filter and go back, and let's say I want to just look at the external API calls I'm making to the weather map API. So I can say sent.api and filter request there. And now here I can see that most of my requests are staying in this under 50 milliseconds boundary, but we've got a couple that have taken a little bit longer. And we can see, again, the timeline it took for that request to go out and the workload that that came from, right? So in this case, it came from the weather backend multiple service, and here's the actual URL it was requesting. And I didn't add any tracing here, so I haven't done anything to my code to enable this. Now, as you can probably imagine, this isn't telling me a whole heck of a lot of information, right? Because Envoy can track those requests from one proxy to another, it's capable of showing you this data. If you want to get that next level of information, if you want to know, well, once it enters that request, once that request hits one of my methods in my, in my code, I want to know which line or which section of that code is taking a long time. If you want that level of detail, you'll have to actually go in and instrument. And you have your choice of different instrumentation libraries, like either Zipkin or OpenCensus, depending on which one makes the most sense for you. But once you have that level of instrumentation, what you would actually see here is a much more granular kind of bar graph of the different sections of your code and how long they took. So you get a much better and clearer idea of what's actually happening across there. The nice thing about that is you don't only have to add the tracing statements into your code. You don't actually have to worry about where to send it. Because again, the proxy's capturing that tracing reporting data on its way out, and it's actually forwarding it onto Mixer, and Mixer is actually posting it to the back end. So that's a quick run through of the tracing components here inside of Stackdriver Trace. Let me quickly show you all what it looks like if you were to look at the open source Prometheus and Grafana. So let me just quickly forward the port over from Prometheus. And I'm doing this from a different cluster that's running in another project. All right, so that's forwarding across. We can open up Prometheus now. And inside Prometheus, if you've ever seen the sort of default Prometheus piece here, you can actually start filtering by Istio metrics. So you can look at sort of Istio total requests and which is not very exciting, right? Looking through all this. It's a lot of information and a lot of data. It's not really sort of eminently visible by default here, even if you kind of graph it out. What's nicer is when you dig into it using Grafana. So the Prometheus and Grafana that come with OSS Istio are pre-configured to be tightly coupled and work together. So Grafana is already pulling data right off that Prometheus instance. So if I do the same thing here, but change that port forwarding to Grafana, I actually see a lot of interesting metrics in Grafana as well. The other nice thing about the instance of Grafana that we package in for you is that it comes with some canned Istio-specific dashboards. So once you load the Grafana main dashboard, you go over to kind of the manage section, which is what I did, and there should be an Istio folder there. You can open that Istio folder, and now we can actually start to say, well, I want to dig into the service dashboard in particular. Inside the service dashboard, right, it opens with any of the services that I'm calling. So because I have a service entry inside of Istio for api.openweathermap.org, it creates a service entry for that here, so I can browse by that. So I can actually see the request volume, the success rate. This one's not that interesting. But if we look at the weather backend, that gets a little bit more interesting, right? We can see the request volume, the success rate, and if we continue on down, incoming requests and response code, right? The success rate, or the duration for some of these calls. Again, highlighting our ability to kind of dig into these calls that might be taking quite a long time, right? This one's showing us that at the 99th percentile, it's returning about 950 milliseconds, which is quite a bit. And there's some TCP-specific ones here that aren't filled in as well. Same thing is true, again, of the weather front end. You can see those dashboards and look at that traffic information. Or you can switch to let's see, where's the Istio workload dashboard? Right, another way to kind of look at the information here. So we'll switch to the default namespace, and we'll look at whether backend multiple. Let's pick on just one of those services. So again, we can see how long things are taking, the duration by source, response size, etc. And we can see all the outbound and outgoing requests as well. So this is built in, right? All those metrics I mentioned earlier, those things automatically get captured by Envoy. Envoy collects that telemetry and then sends it off to Mixer. Mixer forwards it on from you. And if you remember the Istio at a glance image, right, there's a lot of control plane components. And they function very much the same as the Kubernetes control plane does. If one of those pieces goes down for some unspecified amount of time, you're not locked out of the traffic routing, right? You might not be able to push any new rules or new policies while maybe pilot is down, but the rules that were already pushed out and in place, those are still being honored by Envoy. So, right? Just like if you lose the Kubernetes API master for a certain amount of time, your pods and your containers are okay, you just can't schedule anything new. So you've got a little bit of a window of time before things really turn ugly to fix things up. And particularly in the case of telemetry, if Mixer goes down or if you lose access to that Mixer component, Envoy will actually retry to send telemetry, so you won't have these dropouts over time of metrics missing because Mixer wasn't available for some bit there. So can we switch back to the slides? Perfect. All right, so where do you go from here, right? We have a couple of examples or a few examples of how you can roll Istio out in a slow, measured manner across an existing infrastructure or existing cluster. And I would say that the two features that stand out among what we hear from customers and users in the ecosystem are telemetry and security, right? Folks really love the ability to sort of deploy Istio and then get this telemetry information very quickly, right? Because that's quite a bit to be able to use right off the bat. And they also love the security aspect, right? Those two features alone, I think, are enough to make Istio worth it. So what I would challenge you to do is think about, if Istio makes sense for you in a production workload, figure out which of those things make sense. Do you want it for traffic, telemetry, security? And then spend enough time where you feel comfortable with those APIs before you start rolling it out. And do it, again, in that incremental fashion, right? You can actually roll things out and say, well, we're going to deploy it not to the default namespace. We'll do it to a separate namespace, and we'll try things out there before we roll it out to default or to other ones where you might have production workloads. Some light reading to get you started. Megan, actually, who was the previous speaker in this room, both of us worked together on a series of blog posts called the Service Mesh Era. And they're good conceptual overviews, but they've actually got practical tutorials built into each one of those. And they go through a lot more depth here around traffic splitting, canary rollouts, telemetry stuff. There's a security one as well. And actually, the last one in the series focuses on some more advanced topics in Istio, like mesh expansion, adding in VMs, right? We have a lot of workloads that still exist on VMs. I know I went very Kubernetes-centric here, but we want to make VMs just as easy as we want to make it with containers. So you can deploy and expand your mesh now with VMs, but it's still a little bit more work. It's not as easy as just injecting the sidecar. But she's got a great example there. And then there's also examples of running Istio in a multi-cluster deployment, whether you have a single control plane in one cluster or you have multiple control planes. So you can have either one or both of those setups. So that's a great series. I would definitely advise you to take a look at that. And then the traffic portion of this came from a blog post that I wrote a few months ago called Incremental Istio with Traffic Management. So that's another good example. It goes into a little bit more depth of how you could roll it out. And there's also great docs on MTLS migration and some of the conceptual things. The last two links are links to my personal GitHub where I have that weather info app if you want to just have a quick little example. Again, I like that one because it requires you to make that service entry for outbound API access, and it's got a couple other nice little components in there to try out. And then all the stuff I went through, all that YAML that I truncated in a couple of slides is actually in this repo, Next19 Incremental Istio. So it's all there if you want to run through this end-to-end and roll out traffic slowly or roll out some of the security stuff slowly. There's a fully baked example there. Before I close out, I do want to mention a few other talks that are happening tomorrow. These are a little bit more 200 and 300 level, but I think they're really good. Tomorrow morning, actually, Megan and I are going to give a talk on how to debug your deployments inside of Istio, right? So this is an example of you deployed Istio, you deployed your services with the sidecar proxy, and something broke, right? And we're going to take you through 3 or 4 examples of things like how do I debug traffic deployments or traffic errors? How do I debug telemetry? right? What if you have custom metrics? How do you get those to show up inside that Prometheus that you've got as part of open source Istio? And the last one is a security one. We're going to go through, I think, some work with MTLS and JWT tokens as well. So that's very much a demo-centric, specific exercise for debugging, or troubleshooting, I should say. But then we've got a few other ones as well. Particularly, I mentioned the adding Istio for VMs and expanding the service mesh. So that's tomorrow as well. Second to last but not least, we would love your feedback about how to make a better service mesh product, right? We love the input from people who are using Istio, who have played with Istio, who are interested in using Istio. Why? What drives that, right? We want to help improve as much as we can. So this is feedback that we use to make the commercial version better, as well as the open source version. So by all means, sign up, fill out this form. We'd love your feedback and your help. And then finally, also love getting feedback about the session. Please let us know in the app if you found this useful. We'd love to get that feedback. It helps us quite a bit as we figure out sessions for the coming months. And then finally, thank you. I should have mentioned, I apologize, I've got 5 minutes here for questions, for any questions you might want to have. When they kick us out in 5 minutes, I will happily hang out in the hallway for a few. If you want to come find me, I'm happy to answer anything I can. Please, if you have a question, please use the microphones in the middle, just so everybody can hear.
Hey, you mentioned the built-in metrics,
Yep.
which were good. Will those, do those metrics show which services are, like which two services are communicating and what those latencies are and those request durations and things like that?
Yeah, so each one of those things will have like a source workload and a destination workload. So you can see which particular service was calling which other downstream one, and you get the request count between those. So you have the ability to kind of control the in and out there as well.
Perfect. Okay, and then the second question, follow-up to that is, I forgot it. For custom metrics, is the best way to do that just with the metric template?
Yeah, it depends on what your custom metric is. If you need a custom Istio metric, the one that's coming from Istio,
Yeah.
that's the template to use. If you just have generic custom metrics in your code, you can just add annotations to your deployment and push them to that version of, or that instance of Prometheus.
Yeah, I meant Istio metrics.
Okay,
for sure.
yeah,
Okay,
yeah.
cool.
So you're going to use that template and then create your own, metric configuration and push that up. to the
Great. And then
deployment.
does it pull Envoy metrics as well?
Yes, anything that Envoy has, it's basically lifting a lot of the Envoy stuff and pushing that out. So anything that Envoy has access to, you should be able to specify as well.
Awesome. Thank you.
Hi. So one of the problems with Istio adoption is just controlling or defining these service entries for each of your external boundaries. So do you have any sort of recommendation to mitigate that problem? Or to identify those dependencies?
Unfortunately not, right? Like what you ultimately end up having to do for really complex things is almost watching the outbound logs and saying, all right, well, I can clearly, if I grab a bunch of the Envoy logs, I can see there were attempts being made for these outbound services, and then you can capture them that way and sort of generate the kind of preceding YAML that you might need. There are other ways you can do it where you can just say, you can create service entries that have wildcards in them and just say, I want to allow all outbound access on wildcard hosts. So say it again.
And then define SNI proxies?
Can you define SNI? Yeah, you can add that on the other end of that. The other piece, and this is something that's being discussed in the community as well, is whether we should, because right now by default, all egress is blocked. There's some debate going on right now of whether, in a later version of Istio, whether they're going to pull that out and just allow all egress and then let people clamp down if they want to. Because I think there's been exactly that problem of we have too many outbound calls, it'd be impossible for us to figure out how many there are.
Yep. Thank you.
Hi. So we're using the ESP, Extensible Service Proxy, which is also runs as a sidecar. And it does JWT token validation, and it's useful for connecting to cloud endpoints. Mm-hmm. So how do you go about would like auto injection of Istio work in that use case, or how?
See, you can still have the sidecar proxy included there because it could just be right. Your pods can have more than a couple of containers. What I'm not sure about is how you integrate the JOT component. There's a way to do it, but I don't remember where those docs are located. I would say if you can come tomorrow to 303, I think Megan has worked with that a little bit, and she might have an answer for you on that one.
Okay. And then we already have an instance of Prometheus and Grafana running. How do we go about like getting those dashboards that come with the?
So the dashboards, I think there is a Grafana setup script. Basically, if you go through the Helm chart, the Helm chart has the maximum amount of kind of configuration information. What I will often do if I need just one piece of it is effectively generate the Helm chart with Mixer enabled and then Grafana enabled and then Grafana disabled. Okay. Diff the two, and then you've got exactly what Grafana is doing. So you can actually pick and see how that Grafana is set up and deployed, and then just replicate that configuration.
All right.
So you can plug it back into those other components.
All right. Thank you.
Hey, you actually showed some policy configurations for pods talking to each other across namespaces.
Mm-hmm.
And if you actually already are using network policies at the kube level to actually also define the relationship of things that can talk across namespaces, what's the relationship between those two?
They don't really interact because that policy, so there's namespace control policy, which I guess could potentially override that, but you've got, in this case, it's Envoy deciding which thing it's going to allow in. So in that example that I had earlier before, that service that in the legacy namespace was still sending traffic. It was getting out, but Envoy was dropping it at the receiving end. Mm. If you were to change it from the Kubernetes namespace angle, you could say, well, I don't want that traffic to ever leave the namespace.
So network policies at kube level, they kind of supersede. So if you basically have a block there,
yeah,
Envoy's
it's not going to
be able to
communicate, right? Because then Envoy couldn't talk to Envoy there.
Got it. Okay.
They're sort of, it's in one configuration could supersede Envoy, and in another version of it, Envoy can sort of drop packets on the other end, and they kind of intersect a little bit.
For egress control to third-party connected or endpoints, can you whitelist by domain name, or does it have to be by IP address? Or
you can whitelist by domain name, and you can wildcard those too.
Awesome.
So we are out of time. I'm going to pack up my laptop, and I'm going to head out to the hallway, and I will hang out there if anybody's got additional questions. Thank you all.